We're in the SEMC Appion Microscopy Center here in New York. A lot of the technology that we're making use of has been developed through NRAM and NCCAT for the cloud services. We're going to try to make today as hands-on as possible. I'm going to assume that most of you have taken Appion Part 1 and have had no problems. Before I get too far ahead of myself, I will pause and ask if anyone has any questions. We can then resolve that. We're going to go through a quick overview of the single particle workflow, what we're going to try to accomplish today, and how do you make use of Appion to springboard onto some common refinement packages. Today we're going to be focusing on relying on CrowdSpark. We're going to be making use of Amazon Web Services, so everyone will be able to, in their own instance, have a sandbox to play with. And we're going to probably end a little bit early and try to give you as much time as possible. We also have tutorial data sets. We have more than one, so we have a tutorial data set to start you off with, but if you go through that tutorial really quickly, we'll have other data sets for you to try. Okay, so if you don't remember, what is NRAM? NRAM is a P41, that's a National Resource for Automated Molecular Microscopy. A lot of what we use for data acquisition and pre-processing with Legend on Appion is fed forward to what we'll be using today. And a lot of the advantages are that we can forward a lot of microscope parameters, have an electronic record of all that, and jumpstart our pre-processing. I will mention, if you make use of any of the resources here at the Simons Electron Microscopy Center, please do acknowledge us. To refresh your memory, we have two teams working together. We have an operations team, which you can reach us at emg@nyspc.org. We're primarily focused on helping you collect data, sample preparation. The heavy lifting today is really done by our Appion development team. You'll see Swapnil here in the room with us, and he's been doing a lot of the cloud on-demand services that we've been offering, and she is the main curator of Legend on and Appion. And there's a lot of other people working in the background. I will point out that we have a whole host of training programs. This is the second part of our Appion workshop series. Actually today, we have a general user meeting at 2 p.m. So every year we have a town hall where we get feedback from our users. So right after Appion Part 2, we'll have that. And if you're here at 3 o'clock, we also have a picnic for NYSPC, so you're welcome to stay for that. But if you have any issues, we have office hours, Tuesdays and Thursdays at 3, so you can always bring that up. Something that'll be very useful today, everyone should be registered for the forums, the NYSPC SEMC user forums. If not, you can go to appion.org and register with your account. Something that's going to be useful that you can do in the background while I talk would be to go to the NYSPC SEMC user group. If you've taken Appion Part 1, let me actually move this to the appropriate window. If you've taken Appion Part 1, you know this issue, feature 7198. It had the slides from Appion Part 1. It'll also have the tutorial manuals for Appion Part 2. So we have a CrowdSpark guide, we have a Reliant tutorial, and the slides I'm going over are located there. So log in to the NYSPC SEMC user group, and then you can follow along with the tutorials. That may be useful because there's certain commands where you can just copy and paste. Okay, so let's get back to that. So where are we today? Appion Part 2, we're trying to cover perhaps some advanced Appion tools. We'll get to that later if people have questions. And on to the 3D analysis part of the single particle workflow. Basically, how I view it is that once we collect data, we want to generate a stack of particles, also an initial model, and then use that to get an EM map. There are a whole host of programs out there that people commonly use. Today, we're going to be really giving you an environment to play with relying on CrowdSpark, but there are other software packages that can reach comparable resolutions. All these software packages are using different algorithms, and they're widely used in the field, and they're quite useful. It's just a matter of preference in that right now what we have set up easily in our instances are the first two. So if you're collecting data here, a lot of what we're going to go over here is assuming that you're collecting data on one of our instruments. If you're clicking on the TEMs or even an SEMs, you have access to this workflow. Where we are with the single particle workflow, we went over last time what you're going to do when you're actually doing data collection and using Appion for pre-processing. Now we're moving more towards these two columns where you may have done initial 2D classification, perhaps have an initial model. The difference here is you're doing that for efficiency. You're doing it on the fly. It might be binned. It might be on a subset of data. Moving, what we're going to be covering today would be, now let's say you're bidding less or not even bidding at all, and you're trying to encompass more and more of the data, if not your whole data set. And so we're going to go over 2D, 3D refinement. And we're not going to be able to cover model building. That's outside the scope of today. But we're going to try to go from micrographs or a stack of particles, if you've used a lot of the Appion pre-processing workflow, into a 3D reconstruction. So the data workflow, we're going to now shift over to assume that you've been collecting data on one of our high-end instruments. For example, Krios. You're here, you have the web portal that you're very familiar with. In Appion Part 1, we covered Legend on a little bit, and that data workflow. To refresh your memory, what ends up happening, if you're collecting data at the center, you're collecting movie stacks. They'll be in TIFF LZW if they're coming off the K2. We have an ingestion server that will be on the fly doing motion correction, 5x5 patches, motion core 2. It's going to be a global 500 B factor and a local 100 B factor. So then what you'll have from the suggestion server onto the file system are unaligned sums, aligned sums, and aligned dose-weighted sums. In addition, we'll make use of the CPUs on this ingestion server to run CTF find 4, so we have CTF estimation. And you probably have done on-the-fly picking, whether it's Gaussian or template picking. Okay, so this is the stage we're going to assume you're at, and we're going to springboard forward. Does anyone, before I get too far ahead of myself, have any questions about what I consider Appion Part 1? Is everyone able to do that or have the tools to do that? If not, we can cover that. Okay, here is silence. So now let's go forward. So the intention is you have a lot of data on our file system. You can transfer your data remotely via Globus, and what we're really making use of is this dotted line, is the Amazon Web Services and cloud computing, and we'll be making use of a lot of that today. So instead of me going too much on the slides, I have a lot of slides in case the internet breaks down, but hopefully everything is fine. But something that's really interesting that we're trying to make use of is cloud computing. In particular, for this workshop, we're using Amazon Web Services. They have on-demand computational infrastructure that we're going to be making use of. And that is what we find quite economical for people that are occasional users of EM, and also people who are just getting in the field and don't have hardware. If you're a center like us, you would probably get bare metal hardware. You would have a HPC because we're doing processing every day. But if you're only solving a couple structures a year, you may not have an IT team and a whole host of people to maintain your computational infrastructure. So it'll be a little bit easier to just pay as you go. And then when you become experienced, then you know what requirements you need, and then you can convert and actually procuring more of that hardware and software. Has everyone registered for Globus? So Globus is how we're going to transfer data. You can transfer Globus from here to your home institution or here up to Amazon. In this case, for our tutorials, that's what we used. Refreshing your memory, Globus ID is where you create an account. Globus.org is how you transfer data. So let's convert out of the slideshow because I'm hoping I have strong internet connectivity and I can show you certain things on the fly. Okay. So if you log into Globus, to get data from us, it's the NYSPC SEMC endpoint. So if you go to this manager, you can just type in NYSPC SEMC, and then you'll find the relevant endpoint. Here, this one. It's nyspc@globusid.org. That's the correct one. From Appion Part 1, your test accounts are still active, so if you still wanted to do some testing, that is useful. We'll be making use of that account today. So if you go to emgweb.nyspc.org, you can log in with the username test, and the password Appion 2019. It's also on the board over there. Let me circle that in case you can't see. There's a lot of stuff on the board. But assuming you're on Globus, you'll see where your data is. Your data is in 3 different places. It's on our GPFS is this particular file system that we're using. You have an Appion folder, you have your frames folder, and you have your Legend On folder. All the images on EMG Web are located in your Legend On folder. So if you go in there, the user account is test. And if you remember, we had different workshop groups. So the instructor workshop group was workshop I, and you can see there's a raw data, and you can see these are the 10 images that we were using in the tutorial. Great. If you're collecting data on a Krios and you're running the Appion pre-processing, in that same folder, you'll have the Motion Core 2 outputs, meaning the aligned sums that were dose weighted. Okay. The raw data, the raw data, is in your frames folder. And if you look in your test, so here's just a test account. So here is a movie stack. And then within the frames folder, you have your references. And remember, in this case, I guess this is a super resolution data set. If you remember, we have several different gain references. If you're collecting data on a Falcon, that folder is empty because it's gain corrected from the camera, from the system. If you're collecting data with one of our K2 systems and then soon to be upgraded K3 systems, you'll see that the gain reference is located here. There are several different gain references. The norm mod has been flip rotated with respect to the mounting of the camera, so it will match your movies directly. Okay, so each of our microscopes may have a different mounting of the camera, therefore they might have a different flip, rotation, etc. So the mod version, the norm mod, is matched directly to the movie stack. In case there's something wrong with the script, we also have the unmodified version. Okay, so that's in your frames folder. And then lastly, what's in your Appion folder is all the pre-processing. So this is the scratch directory for the bulk of the pre-processing that you were doing during Appion Part 1. So you go to a Workshop I folder, you see the lines, CTF, extracts, stacks, templates, and in case if any of these files are useful, that's how you would download it. You can download it directly via Globus. Something that's interesting in the stacks would be if you create several different stacks, they're actually box files here. So then you have your coordinate picks. Okay. So now that's where you find your data. Let's go back into the web browser so we better understand how we generate all this. Okay, so if you logged on to emgweb.nyspc.org, you logged in with your test account, what you'll see is this page. You're very familiar with this. You can find the workshop that you were working in. I'll hop into I, that was again the instructor workshop. And if we go to processing, we're jumping back into Appion. To make use of Appion, you'll have to log in again. So this login is for the cluster, the Guppy cluster. The first login was to log in to the web Appion tools. Okay. So for example, you have finished your data collection, you have a lot of images, and now you want to begin some processing beyond the pre-processing stage. Okay. You may have made use of a lot of the Appion tools for curation. To refresh your memory, there are features, for example, image rejector, where you can reject images based upon drift, CTF fit, if there's ice rings, etc., and then you can then go in and have basically a list file of images that you want to process or not. Another way would be if you just output a star file with the correct information that you made use of, and there's a way to do that. For example, we have done CTF estimation. You can see there's 2 complete. Here is a table showing the summary statistics. If you scroll down, you can select different CTF runs, or you can select the best of all, and you can download a star file for Reliant 3. So if I just click on that, I just downloaded this star file. What does this star file look like? I can open that star file with a text editor, and that's what a star file is. It's a list of all the micrographs. If you've hidden micrographs, they won't show up. Or if you hid micrographs such that you didn't process it with that CTF estimation run, it won't show up here. And it has all the CTF information. So in this particular test data set, it was collected at 200 kV. The CS is 2, amplitude contrast. Here's CTF information. This is the pixel size. Everything here in the header. So this is quite useful because you can begin processing, let's say, for example, in Reliant and CrowdSpark, skipping a few steps because you already have motion core corrected images. You have a list file with all the CTF information. It might have been pre-sorted to select the images that you would like. Also, you've done particle picking, object selection. So how do you get those box picks? How you get those box picks would be if you've created a stack. So in this case, we did particle picking, and we have several different runs. These are just coordinates, but how do you export them? You would have to go to stack creation and make a stack. You can select the various particle runs, or if you've done cleanup, you can select the particular stack that you like. Don't forget to add a description. You can skip this and only select create eman box files and run that. So then that is how, when I went over here, I created a stack run in this case stack 3. This box files are populated. So these box files are matched to the coordinate picks that we picked in Appion Part 1. By default, Appion makes virtual stacks, so not every stack you make may have box files. And a lot of the cleanup steps, like the mean field distribution cleanup we did, are virtual stacks. So they're referring to a parent stack. And that's for efficiency, because if you just duplicate your data every time you make a substack, then that's a huge expansion of data. Okay. So, but that helps you understand why, depending if you're using an intermediate stack, they might not be located when you go into that directory, because it's referring to a parent stack. So something is like, if you're ready, and all you want is a coordinate picks, just create a new stack file explicitly saying I want the box files. And many programs can read that in. So what I'm trying to tell you would be, what do you have at the end of the day? From Appion, you have box files, you have your micrographs, you have a file that has CTF estimation, so that's sort of a list file. And though you can do initial modeling in Appion, we will do more of that in other refinement packages, for example, in Reliant and CrowdSpark. Okay. So then that helps you spring forward into these packages. So hopefully that orients you that a lot of the work you're doing in Appion you can carry out, and you can begin skipping a few steps. So you don't have to rerun motion correction, you don't have to rerun CTF estimation. You may be able to, or you may want to do that anyway, but if you're in a regime where you're collecting dozens of data sets, you want some feedback to say, how do I prioritize that? And you want initial models, and you want initial processing. Most likely what will happen is, if you have a data set of note that you want to work on, you'll be processing it many different ways in different packages for different purposes. The main reason being, a lot of people are now going after larger complexes, dynamics, and so that lends itself to parsing your data in different ways, because you're not after just resolution as a criteria, you're after biology. So resolution may help inform and be putting you in a better position to answer biological questions, but as we're aware of, your complex is not one resolution. Globally, there might be a resolution, but locally it will have different resolutions. So therefore, you'll be going back and reprocessing it. Okay, great. But how do you know you want to spend the time on this data set versus that data set? So what people find very useful in a very quick manner in a lot of these programs is that you can use the Appion pre-processing that's done on the fly during data collection, and within a matter of hours, get an initial model, an initial refinement, and that can give you an assessment on the quality of the data set. And then you can go back and parse it even further. I did mention some of our default motion correction is 5x5 patches. You might want to do 7x7 patches. You might not even want to do any patches and then do particle polishing, right? So there are different ways of parsing that data. Again, you need to make some decision at some point in time. How heavily invested are you with this particular data set versus another data set, or do you want to combine all these data sets? And you need some criteria for that. And hopefully today we'll give you some additional criteria. So Appion Part 1 was focused on sort of like 1D, 2D criteria. Now we're moving towards 3D criteria. Okay. A lot of what I mentioned, in case you missed it, was this, where do we have the various information, and you can download on Globus. These are on the slides in the forum, so you can just look at that. So today, what we're going to be doing is working with an initial tutorial test set. The initial tutorial test set was collected in 2017. It's GDH. I'll tell you that already that it has D3 symmetry, and we'll be initially processing the dataset bin for efficiency. But if you do process this dataset unbin, you're going to get somewhere in the low 3s. I think people have reprocessed it and gotten sub 3. So the computer programs from when we first started using Reliant 2 to, let's say, CrowdSpark 2.11, which we'll be using, and Reliant 3, there are additional features that you can even push the resolution beyond where we were. A few of the parameters that might be of note would be our dose for the full movie is 35, 36 electrons per angstrom squared. At the time we were doing 400 millisecond frame rate. It was collected in super res, so the bin pixel size in the star file is going to be a little bit different from here because subsequently we calibrated the pixel size. But for the purposes of this workshop, you can use the native, or rather the initially nominally given pixel size. Something of note would be if, let's say, you have a pixel size that is not completely calibrated, so you have a nominal pixel size that's close, and you want to reprocess your data with a calibrated pixel size, you want to make sure you just don't update the star file with the pixel size. You would want to rerun CTF estimation at the new pixel size. If you do that, you'll run into some trouble. So you can do that test on your own if you have time. But that's the main thing, is that certain things that if you have additional information, you might have to go back and rerun. CTF estimation is really quick to run, but it will take some time. If you have 2,000, 4,000 images, yeah, it might only take you a second per image, but now times 4,000. So that does take some time. We're going to boot up Reliant in a moment, but I believe we have the cadre of people who will be here and will take obligatory photos. So we're going to, I'm going to find Kathleen, we're going to take a photo, and we're going to come back in here, and we'll first look at Reliant, and then after the break, we'll move on to CrowdSpark. Okay, so wait one moment. We're going to meet in the control room, and we're going to get a photo. Okay, so let's pose for a photo. Let's move into the control room. We'll look very happy in front of Kathleen, and then we'll come back and be even happier processing. so please close the door. Boom. Okay. So so what has been done for us already is we started up several different instances on the Amazon cloud. We have several different groups. You have IP addresses to go to start up a nice environment where Reliant has already been installed. So again, group 1, group 2, group 3, group 4, group 5, group 6. And then in case you run into trouble, you can always hop into my instance. If you don't have the instructions, where you would get them would be to go into Redmine, find the Appion Part 2 Reliant tutorial. We're going to give you as much time to get used to the environment and get accustomed to certain things, but I'm going to help initially orient you. Here we go. A lot of windows in Reliant. And since I'm split screen, I'm going to have to look at the screen myself. Okay. So there is a command. Let me actually exit because I'll just. So it's SSH-I quotes Appion-2.tem Ubuntu at your IP -XY. So that's for the X display. So then we'll just give you a second. Hopefully everyone has oriented themselves. If you don't know your IP, Swapno's coming around right now to orient you. So then if you hit enter, you'll hop into here. So what is here? Well, we have an instance with 2 GPUs. They're Tesla M60s, and I believe every GPU you have 4 CPUs, or do we have 32 CPUs?
4 versions.
4 times 2, is that 8, or is it 32? So we'll double check how many CPUs we have, but right now we have 2 GPUs. If you type in NVIDIA-SMI, you'll find out what GPUs you'll have in your instance. And then you'll have a little bit less than 256 megabytes of RAM.
32 versions.
32 CPUs? Ah, yes, you're right. So we have 32 CPUs, and we have 240 GB of memory, supposedly. Okay, so this is useful to know because when you're running any program, you need to know your computational environment. Where we are right now is that every group rather has their own instance, and so you'll feel free to play. Something though to make note of, we only have roughly 100 gigabytes of space.
100 gigabytes, yeah.
We have 100 gigabytes of space in this particular instance for you to play, because a lot of the other space was taken up by test data sets and installing Reliant. So you're free to play, you're free to do certain things, but depending on how aggressively you start generating data, you'll max out at a certain point. And in that case, you might have to delete if you wanted to just get a feel for the environment more. So what are we giving you? 240 gigs of RAM, 32 CPUs, 2 GPUs, and 100 gigs of scratch space, not including the, in addition to that, rather, we also have all the test data sets. And if you run into trouble, we've actually already have a folder that has already pre-run all the jobs. So if you find yourself that a job is taking too long or you get stuck, you could always go into a save point and try another feature. If you're very familiar with Linux, this is not an issue. So if you type in list, you'll notice that there are several different data sets. So let's expand my window more because you probably can't see the screen very well. We have the Appion 1 T20S dataset. That includes the 10 exposure images from Appion Part 1. We're not going to use that, but those 10 images can go sub 5 angstroms. Proteasome has D7 symmetry. These are not the best 10. These are just representative 10. If you have a very, very good image, you can actually go sub 3. But we also have the Appion 2 dataset. This is the dataset we'll be using today. If all else fails, we have the Appion 2 group 0 folder, and that's where I basically did the processing that we'll be going through today. For people that are a little bit more advanced and have moved forward, we actually do have movie stacks. So if you wanted to try other features of Reliant, like frame alignment, we have that. And we have a T20S Empire dataset. This is 10.0.25. So that's the T20S proteasome that was solved at 2.8. These are the aligned summed images. And this will give you a larger dataset to play with. The group 0 and the dataset that we'll be using again is GDH. It has D3 symmetry, and in your tutorial it has other information that you need to do. So the main thing is we're going to keep your data files or your data directory pristine, and then we're going to create new directories to work in. And the advantage of that is that you can, so it's really up to you how you want to organize your environment. One suggestion would be keep your raw data in one place and then create additional directories that are named in some way that is intelligible to say that what you're trying to do. And for efficiency that you don't have to copy it, you can always make symbolic links back to the raw data. And the advantage maybe is if you're doing several different runs and you want to separate that, yes, you can annotate that, but you may want to, additionally, create separate folders because you may be dealing with different packages, different complexes, etc. So when you're starting to do processing, data expansion can occur very fast, and you need some sort of naming structure such that in case you don't have your lab notebook with you, or you're doing several different branches, that like, okay, this is a dead end branch, I'm going to work back to some point into the main trunk and then work out again. That's easy to say, but that might not be easy to do. And there may be occasions where you're working on one reconstruction, but actually you have 3 different reconstructions from the same data set, because you might have the best resolution for your pristine global, and then you might do focus classification on a particular part, or you might be doing other refinements to try to push resolution in certain areas, and that may worsen resolution globally, right? So locally you might have better resolution, but then other parts might be smeared out, things like that. So it's not to say that they all can't be in the same folder, but if you do that, then you just have to be very conscientious in annotation. So what am I going to suggest today? Well, I'm going to suggest that you're going to create a directory. So it's like make a directory in this. So let me take a step back. Where are we right now? We're in home Ubuntu, your environment. Let's make a directory that you would find intelligible. Perhaps you might want to say label it as what your group is. Or you make a directory that this is going to be your Reliant 3 demo, and I'm going to be group 0, but you can label your group. Doesn't have to be that, but it's some idea that you have a directory that starts to cue in what's happening. Okay, and we're going to be working in this directory such that we leave all our data files intact. So in my case, I just created a directory called Reliant 3 Group 0. Great. Where is our data? So remember, our data is in Appion 2 dataset. What's in that folder? In that folder, we have micrographs from, if you go to GPFS Leginon and you get your raw data, that's what the micrographs are. We have box files, so if you in Appion created a stack in GPFS Appion in your particular stack folder, you see boxes, so that's what that folder is. In case we don't have time for making initial models, I've already given 2 initial models. One is what I'll consider bin 1, and that is roughly a 0.835 angstrom pixel size at a box size of 288 by 288 pixels. And what we're going to be doing today for efficiency, bin 2, which will be 1.67 angstrom per pixel at 144 by 144 pixel box size. I'm choosing an odd box size on purpose to show you that you don't necessarily have to have 256, 128, 512. Okay. Certain programs allow you to also further bin in the sense that you don't actually have to bin by an integer. In Appion, depending on which program you use, it forces to bin by an integer because not all packages are intercompatible. But let's say Relion or Crossmark, you can actually Fourier bin. So you can bin by a fraction, like 2.5. But this is to show you that you can actually choose box sizes that are more appropriate based upon your pixel size and your protein of interest. Again, how large should your box be? If you have a protein of interest, we say a rule of thumb 1.5 to 2 times larger than your particle of interest. Okay. Now that can be confusing considering if your particle of interest is not a sphere but an oblong shape. But the idea is that that even if it's oblong shape, the box size is large enough that if you don't center your particle correctly, there's enough room to move it around. And note that you might only see the center of it. There actually might be additional features beyond even what you think you see. And we have the star file. So remember, if you run CTF estimation in Appion, you can just output a Relion 3 star file, and this is that. Great. Now, if you want to, you could, in essence, work in this directory, but I'm going to expect that you're going to play around a lot, so we're going to go into the folder that we just created. In my case, I created a folder named as such. Okay, let me even see if I can make this window even larger. Okay, so I'm going into this directory, and there's nothing there yet. For certain files that are small enough, you can copy it. So I'm going to do things a little bit out of order, but everything that I'm going to do is actually in your tutorial. I'm going to copy some files from the Appion 2 dataset into here, and it's going to emit directories by doing that command. But the idea is the star files and certain small images should be quick. There we go. And so what did I copy it over? I copied over some MRCs, star file, and for later, if you do advance, if you want to do something called sharpening, I also included the K2 MTF file. Okay, so what did I just copy over? Star file. So you have access to text editors, for example, V, or you can do Vim if you're used to the Linux environment. Or you can do just something very simple like tail, which just shows you the last few lines of a particular text file. So I'm just going to tail this micrograph star file. And something that you'll note is that the star file gives you a list of the micrographs and CTF estimation information. If you want to use the star file without additional editing, then you would want to actually follow this directory structure. The directory structure assumes that your micrographs are in a folder called micrographs and that you have this as your micrograph. So there may be occasions where you do CTF estimation on your align, some instead of your dose weighted, or you did particle picking on one preset versus another preset. Maybe you did topaz denoising and you did that. So then you would have to make sure that your naming structure is uniform. So if you want to work on your align dose weighted, but you did your CTF on your aligned, you might have to change this name from the align to align dose weighted. So there are certain commands if you use, let's say, a V text editor. You can do something like colon %s, and that basically is searching for a string. So let's say if you only did CTF estimation on the -A's, you might want to replace the -A with the -A-DW, and you want to do that recursively. Don't do that here, but this would be an example of a command that you can find and replace. So this would be in a particular instruction of note, because what we standardly do here is do CTF estimation on the aligned sum and do particle picking on the aligned dose weighted sum, and recommend that you use the aligned dose weighted sum for processing. Okay. There are ways around it. So you can transfer your CTF estimation in Appion to another preset, and then you can just download that star file and it'll already be in the right syntax. You can also use a text editor to do that. But what I'm really trying to tell you is that if you want to use the star file outright, you have to follow the right nomenclature that is used here. Okay, and if you don't know how to do this, we can go over this during your practical free time. Okay, so because of this, I'm going to try to preserve that naming structure. If I don't like that naming structure, then I'll just update the star file to the structure I would want. But in this case, I want to create a folder called micrographs. And because my star file is assuming my micrographs are in a folder called micrographs. Okay. I don't want to waste my 100 gigs of hard disk space. So what I'm going to do is I'm going to go into the micrographs folder, and I'm going to create a symbolic link to the micrographs. And where are the micrographs? Well, so if you can't see what I'm typing, it's also in your tutorial, and you can even just copy and paste that command. So you want to symbolically link from wherever your micrographs are into this micrographs folder. And what you should have are symbolic links to that. So let's see. In this case, we have 500 some micrographs. Okay. And I'm not copying it, I'm just making the symbolic link from wherever they are, such that when Rely looks into this folder, they'll go to the appropriate place. Whoops. Right, so if I actually list, I can see, like, despite that file there, it's actually pointing to the appropriate place. Something else that I'm going to do, you don't have to do it this way, there's several different ways of doing the same thing. Box files are small enough that you could potentially just copy the whole directory into this folder. But in this micrographs folder, I'm going to also copy the box, or make a symbolic link to the box files. It's going to be called boxes. And I'm actually going to call this, well, my notation would be, I'll call this micrographs. So this is a little bit strange. I created a micrographs folder. I symbolically linked all my micrographs into there, as well as a box file named box file folder named micrographs. Whoops, I actually misspelled it. I forgot no. Over there. Okay. So it doesn't really matter. There's symbolic links. I have a misspelled one, but in this micrographs folder, I have my micrographs and box file, which I labeled micrographs. Great. If I go up a folder, I can see what I have now. I have an initial model, my star file, my micrographs folder with micrographs, and then also in there a folder called micrographs, which are actually box files. Within this directory, we're going to start up Relion. How do you do that? You just type in Relion in the command line. So just make sure, if you're ever uncertain where you are, you can type your path. So right now my path is home Ubuntu Relion 3 group 0. That's the folder that I created where I'm going to do all my work, right? And you could always make sure that everything is appropriate. Okay, but this is the folder you created. This is where you want to start Reliant. And it'll ask you, do you want to start Reliant here? And you say yes. Hopefully you have Xdisplay running, and what should appear is this GUI. We're running Reliant 3.07. You can start following the tutorial, but I'm just going to orient you. So if you were to use Reliant from step 1, you would start here in this panel here and import micrographs, whatnot. By using the Appion pre-processing, we're actually going to start Reliant here in particle extraction. So we're going to browse, and it has something called nodes, but we know exactly where we have our data, right? So it's in home Ubuntu, the folder you created, so you can just go there, and we're going to find this micrograph star file that we downloaded from Appion, and this is the list of micrographs. And we already have coordinates. The coordinates are micrographs, and they were output as box files. So now you know it's just my naming structure. That's why I had you set up the environment as such. You don't have to necessarily do this. You can have your own structure, but and you can change the star file as that. But I put the import coordinates in a folder called micrographs, and then the extension for the particle pixel.box. Right. The rest of the tutorial will you can start working on your own. But the main thing is that what I wanted to orient you would be, here are several different jobs. There's several different tabs. The first tab usually is where you set up your job. In terms of the extract, just note that the original particle pics were 288 pixels. So you can potentially rescale to any particle size, but if you just want to do a straight bin 2, it's going to be 144. And that's what I'll suggest you do for this initial tutorial. And for the running tab, certain processes are CPU based, certain processes are GPU based. For example, this is a CPU process, and so remember you have 32 CPUs, so you can run it with 32. Okay. Maybe you can run it with 33 because one is the master and one's the slave. Anyways, so when you first create a job, what you'll see is, based upon this job, it'll have a root name. This is job 1, and it says that's the extract job. You can do certain things like, I actually want to change the name of this job. I can change the alias and say this is GDH bin 2 or whatnot. And so you can now change that, so then this alias is in the file system still going to be job 2, but or job 1 in this case, but then this can be labeled as something more intelligible. In this panel, you see the number of jobs that are running. In here, you'll see basically if you double click on here, this is a text file of the run.out, and it'll give you an indication of actually the output of it running. If there are any errors would pop up here. And there are certain known errors. For example, not every micrograph has a box file. Right, so certain things are errors that are not gating that'll still continue, and you'll see that here. And so this might take a while, depending on how much you have. And you don't have to necessarily work with the full data set. You might work with a partial bit of the data set. So from here on in, you can follow the tutorial in the sense that first is we are starting up here, and what would you normally want to do? Well, what you normally would like to do would be to do some 2D classification, maybe generate an initial model, but in this case, for time's sake, you can do that later on. We'll have the instance open all day, so for the first part we're going to go over Reliant. We'll take a break, obligatory pizza. You don't have to eat the pizza. And then we'll hop into CrowdSpark. And then just to give you an intro, at the end, before we take a break, I'm going to go over each of the modules. And you may not be able, within the time allotted, to get through the whole tutorial, but I'll give you a snapshot of the results that you would get. We'll come around and see if there are any issues that you run into. But the idea is for you to start using this as a practical, not by me just saying, take your hand, move it here, and press this button, but for you to have a data set that you can play with. If you don't feel that you want to work with the GDH data set, I did point out you have a couple other data sets that you can play with. And that's if you feel that you're a little bit more advanced, then you can try other things. So you can try other features that I did not cover within the tutorial. But the reason why I'm going to ask you to skip is that I also here have an initial model, such that if you want to hop into 3D classification, there's this file right here that you can use as your initial model. Okay, so again, the tutorial is in front of you, and if not, you can go to the Redmine issue, and then I'm going to have you just start going as far as you can. The goal would be, after you extract some particles, would be to do 2D classification, and there are a few options within the tutorial that you can do 2D classifications, and when I go over the overview, I'll show you the results of both. And skip initial model, and you can decide if you want to do 3D classification or you want to do 3D auto refine, right? But at minimum, what I want you to try to do is 2D classification and some parts of 3D, whether it's 3D classification or 3D refinement. If you have additional time, you can try certain things. Given that we don't have movies, you won't be able to try Bayesian polishing, but if the instance, again, will be left open for the remainder of the day, and if you want to go to the not Empire dataset, but the movie dataset, there are actually movies that you can do particle polishing. So what's particle polishing? So right now, Motion Core, we assumed we had a movie stack. We did not only whole frame alignment, we did it in patches, right? So now, if you want to go beyond that and on a per particle basis do motion correction, you could. The main thing is then you need the parent movie. In this case, for the tutorial, for efficiency, we gave you the align sum. So you would, in addition to that, need the movie, which we did not provide for you, but we did provide a movie for another test data set. Okay. So this is a really brief introduction to the Reliant interface, and the main thing is that given how long this is taking, this takes 10 minutes to extract, you may opt to even bin more aggressively. Or not. Or you may decide to shorten your star file and just say, I'm only going to use the first 10,000 particles or whatnot.
I think yours might be slow.
I think mine's slow. You might be done
Yeah.
already, right? I might have a slow instance. So this is a good good point. Normally it would finish in 2-3 minutes. Maybe your instances are a little bit faster, so you should probably most likely extract it in a couple minutes. Okay, so we're going to go around. You're going to start following the tutorial, and hopefully you run into errors, because that's the point where you can get help, you can explore the environment, see how the GUI feels, know how to submit jobs. Right now, only submit one job at once. So the last thing I went over is, or I'm going to go over, for extraction, you're using CPUs. How do you run a job with GPUs? Let's say auto refine. You'll need an input star file, a reference map. So again, by default, it hops into a known structure, but you know where you keep your files. So in case it tries to, for ease of use, hop into an alias that was generated within Reliant. But since we preceded your folder with certain files already, you would have to explicitly go to that file path and find something. For example, if I want to do 3D refinement, I would use, and I extracted my particles at 144 pixel size, I would use this reference model. Okay. So now what I really want to go into is this compute tab, where given we have a certain amount of RAM, this instance is SSD, so it runs pretty fast. You won't have any I/O issues, so it won't be a bottleneck. But there might be occasions where you want to pre-read your images to RAM. Just note how much RAM we have, 240 gigabytes. So if you extracted your let's say you extracted your particles beyond that, then it won't be able to be used. Something you can do for speed is to skip padding. But the main point here is if you have GPUs, you want to say GPU acceleration yes. A reminder, we have 2 GPUs, so we're actually going to put 3. So one is the master node that's going to send commands out, and 2 would be the workers, which are the 2 GPUs you have in your instance. So if you're running certain features in GPUs, then you just want to make sure in your compute tab you do select GPU acceleration, and then you select 3 MPI processes. And then certain classification runs, you have the option in optimization to use fast subsets. You want to say yes, because what that will do is it'll use an initial subset, and then every iteration it'll bring in more and more particles. The advantage of that initial seed is fewer particles, therefore the beginning iterations will be faster. It's not using the full data set. So there's some times where you might want to use a full data set, but for this particular data set, it's a good test sample is D3 symmetry, and you should be able to use fast data sets. Something that we are not providing with this environment is a nice visual display. We don't have Chimera installed, so a lot of the 3D visual display is left to be desired. So for example, in your tutorial, you'll see that if you want to see a 3D output, it's 2D slices of a 3D projection. But I try to show you in a couple places, if you ran ab initio or initial model, what that would look like. And in your tutorial, if you ran initial model, like these would be the outputs you would see. So in lieu of you doing that, we have in your tutorial certain examples what you would see. When we move on to the CrowdSpark arena a little bit later, you'll be able to download the models that you generate and view that in Chimera. Okay, so now it's time for you to get used to the environment and see how far you can go through the pipeline and understand Reliant. So if you're using bin 1, you probably will get to low 3s. If you're binning by 2, you should get to the mid 3s. So it's a pretty good data set, the GD8 data set. Is anyone not able to start Reliant? Not able to get to our environment? Start a 2D classification, and we'll see how long certain
But Ed,
yes.
the number of box files and number of micrographs are not the same, right?
Right. So,
you
we have more
Micrographs.
more micrographs. And so what we were doing is that we did CTF estimation on the full set, but we hid some images. And when we created a stack, it skipped hidden or rejected images. So therefore, the box files are much less than the full micrographs. That was on purpose. So that's another way. So if you've done micrograph curation, there's different ways of applying curation. So, I mean, if you just literally didn't copy that micrograph, that's easy. Or if you did copy the micrograph and you want to work on a certain subset, how do you mark that?
Mm-hmm.
So sometimes our instances might feel faster or slower. If you feel that certain steps are just taking too long and you want to move on to the Appion to group 0. So if you type in rely in there, you'll know that many steps have been pre-run. So if you don't want to do particle extraction and you want to just start from there, you can go there. You just have to make note that you're going to start at job 15 moving forward. Or if, let's say, you're just doing something like, oh, I'm running out of time, you can just say, I just want to see 3D refinement. You know, you can just jump into that.
Is the mask diameter default of 200 okay?
That'll be fine. Yeah, fast subsets. Already on iteration 9. Great. How's our load? How's our AWS load?
The load is normal, I mean.
Okay.
Measure the window.
We just physically type in there, microcloud. So we can say
It's about
it's a
the
browser.
maybe the network connections, because I think we are only using one. Should we split it?
Does that impact? And it doesn't impact processing, right? It only impacts when we go into CrowdSpark, it'll impact display.
The display as well as, because the instances are on the cloud, right? We are sending command.
Okay, so in SEMC guest workshop.
Some serious time.
Okay. So in case your Wi-Fi is slow, we have another Wi-Fi router point, and it's SEMC guest.
I selected yes, where is it here? But no. I'm just gonna copy this.
And the password should be workshop. The difference is that there's so many people in the workshop, so it might end up being a little slower.
I just can't find the files. So
Okay.
I'm trying to pause it from here.
So you might not have copied the files, so you can always copy or DVD it. If you list in group 4, you see. Yeah, okay, so what we want to do is we want to put these, so based upon this star file, right, it wants to have, let's say, this micrograph here. And that looks fine, right? It finds it. You also have it in multiple places. I guess you copied it there and there.
Maybe I should do it always. It's already there.
No. Okay, so what you have to be careful about is that your directory structure. So right now I'm linking a couple up, but if I move this away, the way that I symbolically link it, it wants to go up 2 directories. So then if I put it in another directory, it'll go up, but not enough. So something else you could do is, instead of linking, you could like explicitly link it to the full path, and then it would have that. So even if you move the folder, it won't come into trouble.
Or an array of things in the box.
Okay. Anyways, doesn't really matter. You have duplication. You have a star file. Okay. So what do we want to do?
So now we're like,
Yeah, it's there.
No, you don't, you can just type it out instead of finding it, and then I'm gonna suggest that you then.
That's the one you wanted, right? Yeah.
No. Very soon is on a little left. Okay, so now if you click on here, it takes some time to run, but in here, it'll show you what it's doing. And this is not the calibrated pixel size, but it doesn't really matter for the tutorial. But if you click, okay, it'll take 5 minutes. Or less. So it's half the time. It really depends on your instance. So you can see, like, it took me 9 minutes, which is only take you 4 minutes. When I ran it, when no one else was running it, it only took me 2 minutes.
Okay.
So,
Okay.
How do you know it's actually running and not just stalled?
You can click on it and it should update. Another thing you can look at is, so it's a funny thing where when something is running,
Yeah.
you'll see this mouse here, and it's going to go towards the cheese. But then you can also go into the folder. So if you go into your Appion folder, it's explicit, right? In this case, it's in class 2D, whatever that is. So if you go into there, you can see the timestamp of the output as well. Another thing that you can do is if you look, since everyone's running it interactively, if you top, you can see if there's any Reliant processes running. But normally, as you can see here, like this iteration, it's moving, right? The number is changing, and it's moving forward.
I don't think they're not.
Yeah.
But then if it's an error like that, then it's probably stops.
This error code.
Well, then it's not running. It's an
Yeah.
error.
So if it,
Okay, so then let's click on that job.
what's that?
Yeah, and then let's go through the tabs. Okay, using the extract folder, great. Optimization, great. Not. Compute tab, okay, great. And running tab, fine. And then let's double click on that error code. And then maybe when it goes.
So I didn't link the directory, so that's why it has a problem to find the directory.
Interesting. So when we close out a Reliant, type in NVIDIA.dash.smi.
Your folder, there's home.
Let's
No.
see if you actually
It's just
see
in the
the
find
video
the
card.
files because the
Okay,
file is
okay.
safely in another
Well,
directory
then
and
you
we
can-
link because we don't want
They look
copy
okay.
to be backdated.
They're not
Yeah.
running anything. It says
And
no
the
running
folder,
processes
so
found.
we
Let's
just
set the Reliant
link
again, and
them,
let's
but
just
I
try to run
didn't
that
link
again.
correctly, that's why it had a problem to find the files.
So if you just click on that, and then you click on 2D classification to try to run.
So from there, and I have that.
Oh, it remembers what we put.
Yeah, because you have lots of background.
Yeah.
You don't want, you just want your
Let's see what new error. It could also be the instance. Ah, okay, let's see. Abort MPI processes. This particular instance doesn't like it. It's getting an error, Reliant error.
Yeah.
Yeah, we have to check the IP and see if everything's linked appropriately. That's why we also have a spare IP.
It's the number 5.
So now you understand we have to get the environment linked very well. So sometimes these instances don't show.
What's your problem?
What? What's going on?
That is.
Well, let's see. Your file's not there. That's correct. Okay, so let's look at your directory structure. Right. So if you look in the micrographs folder,
Yeah.
it's empty. So another way of doing it, so we're going to use this.
Oh, so I have to relink it every time I start because I had to restart. Or no, is that not?
No, you linked it into the wrong place.
Really?
Um,
Okay.
So if you go another way, it'd be like, okay, I'm expecting a micrograph here.
Yeah.
So if I go list, no such file of record because it's not there. Where is it? It's one up. So if I move, well, I don't know if that would work. Let's see if that works. Into micrographs. Now they're there. So now if I list that, they appear. It's actually existing. So rely on brand, it just didn't find. So if we double click here, it didn't find any of these, which is fine. So then it just skipped it. So now if I continue, we'll see if it finds anything. Okay, it didn't find that. Okay, let's go see. Micrographs. And we'll rename that micrographs. Let's run it again. So basically it ran again. It didn't find any files. In relation to that star file. So that's why you just have to match the syntax. So now it's finding. So this is what I mean. Here's a mouse, here's some Swiss cheese. The mouse is going towards that cheese. And for you, it will take 5 minutes. Okay, so my instance is extremely slow. Everyone else's is really fast. It just takes like,
And ours doesn't run at all.
but yours doesn't run at all. So then the other thing you can try is run in CPU.
Oh,
Okay,
okay.
stop that.
You have RAM?
Yeah.
There's a similar different
No? 240? Cool.
Let's see. What we have. Okay.
I don't know what this
Okay.
Appion
And
The GPUs, I think.
RAM 1 and GPU 1 through RAM.
Okay, check. Are you able to run the GPU jobs?
Yeah. But it's taking a lot of time. I don't understand why.
There's a
13 minutes
2
pro.
case
I
with
tried.
GPU. We can try both actually.
Did you try to rerun the job?
Sorry, again, say again?
Did you try to rerun the job?
Yeah.
Still gives the same error?
Oh, you want me to rerun it now?
Yeah.
We can stop that or you could run it. Unfit. It's gonna take a little bit longer.
So inputting the proper parameters.
The box files, so you just specify box files to be in a folder called micrographs. So you would have to change that name. So if you just link the box files with boxes, then so either you change it in the GUI or you change it in the, it doesn't matter what, it just has to.
I don't have
If it's boxes, then it will go into a folder looking for boxes. Box. I just kept the micrographs because it's my naming structure, but you don't have to do that. It just has to mirror. It has to be wherever it's looking. It has to be there.
It says MPI, I think, but I checked the instance. It has MPI.
It has MPI. So you don't have MPI. You don't really have MPI. So you can't even run CPU.
Acceleration.
No, it has.
It has MPI. Okay, let's see. Let's see if, let's say we did this. We did no. Will this run? No, the question is it a GPU thing?
Okay, now we, oh no.
No, it's I think it's an MPI issue in this particular instance.
And then just wait. And we have 3.
Yeah, it might be this, so we might have to give you a different instance. Oh, no, you didn't extract any part.
We didn't expect that.
Ah, that makes sense.
If you're on it, right?
So it's like
faster. It depends how.
Yeah,
this,
how
this,
full
this.
your computer is.
I think the circuit.
Just looking into something that doesn't exist.
Oh no.
Hence, that's why it's all red.
And not theoretically,
Why
we
is
should
it
have
so
something
slow?
like that.
Yes, yes.
We rely on these tests.
So I guess it's
You should be really fast.
Doesn't take so
when
much
it's
time,
second.
but when you have like so many particles, it takes time.
Final specification, now we can go here, and specification output. Model star file in display.
Okay, so if we run this again,
Unless it's again around its rinse off, no? It did not work.
okay, here's the cheese, here's the mouse,
Yay.
and it will take 3 minutes.
Okay, thank you.
So what are you doing?
Well, let's see. They
Here's
didn't.
the
They didn't
One by
extract
one,
particles
they
yet.
take
So let's
one
see
by
if they have particles. If they'll still have that error. So I think the error is that it
So
looked
this is
into
probably
a
the
place with
slowest
0 particles.
one. Most of all.
Yes, but this is the point of the silly things and just get it set up.
So F,
Yeah.
then this is wrong, right? Then
No, that's what I typed in.
there.
Or 8 seconds.
But we had
So it's
boxes
couple
now,
minutes.
right?
Couple minutes.
No, so if you understand, this is the exact command.
But, hold on. Yeah, who can read has this has advantage. Not here, there,
Yeah.
right? So
Yes, yes. So then it depends on what it's called. So
Yeah.
so so that's a syntax thing.
Yeah, read terminal, don't read line. Thank you.
Alrighty. So if you're starting to run 2D, you can display. So even though this display doesn't have everything, you can go to File, Display, and you can see intermediate runs if you're running. Let's see if I.
The final result. Plus 2D.
Jump 2. Oh yeah, yeah, this is
I can set my display not to fall asleep.
select the model star file. Model star. So it should be
Model star, so it will be this one. This is the latest. This is the latest version 9.
Let's give 15.
No more than 20. 10 to 20.
display.
Yeah, no.
Here is no.
No, sorry.
So,
Well, patience is fine.
At least
Oh.
it's low,
close to
still
here,
more.
we still need to wait. So.
So I only did 20 iterations, but if I want to display the model,
Halfway.
model.star, I can see the current status. Ah, it's over here. It takes a while for my X to swipe. Here we go. I only did a few.
Oh.
It's a little clunky, so like let's say you want to scale, let's say you want even larger ones. You can do 2, and it'll be even larger.
or if I want it smaller, I can scale it. Damn, it's so tiny. So the first 5 or 10 iterations, it might not look like that much, but after that, you'll start to see pretty good alignment. So the question is, how many iterations are enough for convergence? Well, you may not need that many iterations. Something that you could plot to say, like, okay, do I need 1 iteration, 10 iterations, 100 iterations? If you click on this run out file, you'll see that it has certain parameters like current resolution, accuracy of angles, offsets, etc. You can plot that over iteration, and you can see what should happen over time. It plateaus. And so once you plateau, that potentially could be sufficient to stop. So even though the default is 25 iterations, you might be done in 10. You might need 100, depending on what your data set actually looks like. But the purpose for 2D classification, I tend to be very generous, is for this. Though despite us picking certain things, not everything is a particle of interest. So you may be able to sort out, classes like this, where you can say, well, I don't have any particles of that, so I don't want that class. Be careful. This is classification. This is not pure particle sorting. Meaning, within even this class may be particles that look good, and within this class are particles that look bad, because it's just an average of a certain number of particles. So if I have 1,000 good particles and 1 bad particle, well, this class will still look like this. And so that's to say that you will be able to do some amount of sorting, but it's not perfect. And 1,000 to 1, maybe that's okay. But at a certain point, you would probably need more classes to do that in a more refined manner, to say that, okay, I really want to focus on certain particles versus another. Now, 2D is imperfect. What is better is 3D information is better than 2D, which is better than 1D, right? So 2D can, I caution you during Appion Part 1, I'm cautioning you again that you can do some particle sorting, but you may not have sufficient criteria to, at a 2D level, really sort things out. I mean, if it's like whole edge, ice contamination, yes. But you might have a situation where you're like, this looks like a particle and that looks like a particle. In that case, I would keep both. And then go on to 3D and try to use 3D classification as a potential additional criteria and information to start sorting out particles. Again, the issue is not necessarily object selection, it's particle verification. And especially if you're working with a complex, it can get tricky because you're trying to verify the core would be the same, but you have a judgment saying like, okay, this has 5 components, that's a particle, this has 4 components, that's not useful for me at all. And that can be quite tricky to really tease out. And that's why you would have to move on to, let's say, 3D. And that might be insufficient, and you might have to do some more analysis, like focus classification, like focus on an area where that particular component is or is not. Right, so that gives you more of a, a softer approach where in initial phases, it's actually okay to be very brute force, to say, okay, very black and white, saying like, okay, this is a particle, this is not a particle, this is what I'm interested in, what I'm not interested in. However, as people work on more complex systems that are with greater dynamics, it becomes very tricky to sort out what is of use and not of use. So right now I'm relying in 23 out of 25 iterations. if I feel that that's enough, I could actually stop it and just move on. And for the tutorial, that's perfectly fine. You know, I can just see what the processes are going, and I can just kill. And what will end up happening is if I terminate a job early and I select it, it might come up with an error message like, it ended prematurely. But I might say, that's fine. I actually only needed 20 iterations and I was perfectly fine. You could always go in and say, mark it as finished. Or you can say it's not finished. So it's sort of up to you. So don't feel that I said to say do 50 iterations. I have to wait for 50 iterations. Or it might be the situation I did 50 iterations. 50 iterations are not enough. I need more than 50 iterations. You can always tell Reline to say, I'm going to say that I've only done 22 iterations because I killed it before 23. Resume starting at 22. And then in this case, if it's only done 22 and I said 25, I'll only do 3 more. So if I actually wanted to do 50 iterations, then I would have to say, okay, you're going to have to do 28, 26 more by doing that. And then you can start that again. Or I can say, I like it. I'm going to just go, and I feel so bold to say that even though it's not finished, I'm going to use this classification to sort particles. And I'm going to just display them. And I'm going to select what I like. Okay, this is tiny, so let me expand the display a little bit larger. So you can say like, great, I see a lot of secondary structure detail. I like this class, I'm going to select that class. And this is where a 2-button mouse will come in handy because Reliant has 2 features. One is display, and one is where you actually select classes per se. And in that case, you would say you select a certain amount of classes, and if you do your second mouse click, you can show data. For example, I selected 21,000 particles of that. Okay. You can see, or you can just select each particular class and get some statistics. And then you can save selected classes. If you just go into the display, this is grayed out. Okay, so if you actually want to, let's say you did classification, you want to save those classes, you have to explicitly go into this subset selection job, pick a particular star file and run it. Something that may happen is that your particle picking object selection is not very, very good. You may have duplicates. So something that's also useful is that if you have a subset selection, you may have duplicates where you can specifically say, I want to remove particles that are too close together. Basically, if here's my particle and I picked here and I picked here, well, I'm actually double picking the particle. You just want to pick that particle once. And so the defaults are pretty good, where in case I did any double picking or I just picked too close, where I might pick a particle but it might align to the neighboring particle because I centered it so poorly, or it just was never centered in the first place, you can do that. So if you already have an existing star file, you can choose a star file. In this case, I'll choose a selected star file and I can say, yes, I just want to remove duplicates. Particle star files. Not this one. This one. And it'll remove duplicates. In this case, it picked really well. There are no duplicates. What happens if you add a lot of the same particle multiple times? Well, in that case, a particle correlates with itself really well. So when you do some of the validation techniques, you'll notice very odd correlations because eventually what will end up happening is an FSC is a validation technique for similarity. If you have a lot of like particles, you'll notice that
your Fourier show correlation never drops to 0 because there's complete identity in not only the noise but the particle itself if you just have multiple particles in the reconstruction. So there are things like that. So I'm skipping a lot of additional features, but there are a lot of additional features in Reliant that you can also look at. But great, I have a certain subset selection, and I can decide I could do 3D classification, or I can be so bold and, again, just go straight into 3D refinement. If you're skipping initial model, which we are for efficiency, then you can use this reference map. If you do use a reference map, do low pass filter it, and you have the option of applying symmetry. Why do I want to low pass filter my reference model? So if I have white noise and I give you a 3 angstrom reference model, you probably can get back a 3 angstrom map by aligning white noise. That's very dangerous. So just the same thing with template picking. Why do we generate templates from the data set? It's a data expansion. Why do we low pass filter a reference model? So if I low pass my reference model to, let's say, 60 angstroms, and I get 3 angstroms, well, my search model, my reference model, doesn't have that resolution. So any resolution I gain is not coming from model bias. Okay. So there's certain things like we do that. So the reason why I'm pointing out is that it's very easy for you to artificially process data in a way that you have a good number, but may not be meaningful. So we're trying to point out certain pitfalls that you might get into because you're just not aware of how the algorithm is necessarily processing your data. Some packages by default already pre-process or auto-fills out certain steps that you never have to worry about, I'm accidentally going to introduce model bias or process the data in a way that would lend itself to misinterpretation of the data. It's not foolproof, but you want to be aware of massaging your data to get more information versus massaging your data to optimize criteria which is completely decoupled from answering a biological question. So this is why I caution, resolution is a good criteria to optimize on, but if your ultimate goal is a biological question, resolution can only get you so far, and you need orthogonal information as criteria to focus on the right areas of your macromolecule to see if whatever you're doing in the processing steps is actually giving you a better result. So there might be an occasion where you have poorer global resolution but better biology. And if you're after biology, then that is what you want to go through and go for. So in this case, I'm going to begin a refinement run. I'm running it because I just want to get an estimate of how long certain steps take. So if you don't get as far, I don't expect you to. But if you do get further, then that's great. So we will have a working lunch, meaning we'll power through and continue on. So what you can do is, if you want to start gathering pizza in about 10 or so minutes, I'm going to go over certain results of Reliant, and then you have the luxury of also playing some more. In about a half an hour, I'm going to convert into the CrowdSpark tutorial, and then we'll work with that. The Reliant, given that you're working in pairs, the Reliant instance will still be kept open for a few more hours, so you can start doing the rest of that tutorial concurrently or after. But the main thing is I want to introduce you to Reliant, I want to introduce you to CrowdSpark. You have the same data set in both, and then that allows you to sort of now compare and contrast. I'm doing certain steps in Reliant, I'm doing certain steps in CrowdSpark. They're not exactly one-to-one. So particle construction, fine. CTF estimation, fine. But initial model in Reliant is not necessarily the same as in CrowdSpark. Classification in Reliant is not exactly the same as CrowdSpark. It's not to say one is better or worse, it's just that you would want to know what each program has to offer, because each program treats data slightly differently, and you can get a comparable result. And so I just want to give you enough time to play with both, and so you can start comparing and contrasting the same data set in both. And in the case when we convert to the CrowdSpark data set, I'm already going to assume that you've done particle extraction in Reliant, and then that's where we're going to jump off into CrowdSpark, that you've already extracted particles, and it'll actually be the same exact data set, and you'll have a star file that was generated in Reliant that you'll be working in CrowdSpark. So if you want to grab pizza, you can. If not, then in about 10 minutes, I'm just going to do a wrap up of Reliant, and then I'm going to pause for a little bit of a break, and then I'm going to begin the CrowdSpark tutorial. Again, the idea is that you have an environment, you have a data set, and you can just start running jobs. And you can start running jobs out of order when I go over the review by hopping into Appion to group 0, where things have already been pre-run, and then now you can start seeing other features by just making use of already generated outputs. Anyone stuck somewhere? Stuck. Good. That's a good thing. So let's unstuck. Unstick.
No matter what I do, it's not my
Okay, so there was a typo in the instructions because it's actually boxes instead of box
You can
files.
run afterwards classification too, but we have to select good classes.
You're running, can we see display?
So that's the range of when you see.
Oh, okay. I mean, can you 6 more minutes? This one.
Pizza time.
I don't know, so you can
Yeah.
Yeah, that's two class.
So you just have to
So
move
after you're
your
done with
entire-
this step, we can see this step.
Yes, you read the classes.
Yeah, I think so. Yeah, otherwise you can be getting garbage.
Perfect one.
It just what happens so when it's kind of slow.
And so you have something called as the model load step.
You have the first one.
This is the one.
reference one, in case you want to do
And then so there's
three.
no ones.
I have an option of sorting it. This is good, this is good. Wait for some more iterations. Kill the short.
Running. Here's a mouse. Here's
Oh, so you
cheese.
got it stuck.
And I think it's running now.
It's going fine. I have to restart.
Well, it'll
Because I'm
find,
staring at
no,
mine.
it'll know that that's the extension, so it'll go in there. So that's this is a little bit odd, that's just a syntax
It's
of
like small.
Reliant.
the particles
But if
in
you
RAM.
were to say import,
But
then
here
you
we
need to
can
want the
do
particles in RAM.
so that's like the very, very
So
first.
it's much faster.
How do you usually
I have an option here. You can pre-read all the particles in RAM. If you have this number of particles, probably
You may have only done one class.
many people don't know it, but
That's
it
fine, so
says
if you go into 3D classification, and you go into your optimization tab, you chose one class. That's fine, you might only need one class, that's okay.
sleepy.
Yeah.
Way to kill us all.
Oh, you're done? Okay, so,
Not yet. We're 25.
but you want to kill it.
Yes.
Sure, it would be
Um,
very big.
and then what you'll see like
it died, why?
and we told it to, and then I can just say, okay, great, it's done. Now you can just move on.
69 iterations.
Okay.
But it's, they're doing concepts and so it's using 17,000 multiples.
Mm-hmm.
So this was
Choose the symmetry.
So will you choose the extract the nanoparticles? I mean, so you can choose a part, or you can choose small part or large part.
you are accept the particles.
Yeah. So I mean,
You
it's
can
similar with like our chemical synthesis, you know. Sometimes if the yield is very high, we will use that data. So sometimes if it's low, we don't use that data for population. Yeah. So it's a
Waiting for skills. Theoretically, this is not going to be incredible.
Not very sure, but I guess it's fine since it's useful and doesn't come out here unless
Or well-known structure, so you
okay,
can
add it here. So, I wanna ask one question, so the number of classes is one?
Oh yeah, so you have to change the number of classes. So if you only select one, you only have one class. If you select two, you have two. If you have 50, you have 50.
Okay, so.
But it's based on how you think, how many different type of particle you have in the system.
You can always, well, in this case, you might only have 3 or so views. If you only have 3 views and I specify 1,000, those 3 views will be represented multiple times.
Mm-hmm.
It also depends on how much noise you have, because if you have a lot of junk particles that can align to each other, you'll have more than just a minimal amount of views, including symmetry. So D3, yeah, you'll have like a 3-fold, you have a 2-fold. So technically, okay, you might think you have 2 classes, but if you also have junk, junk might not actually be random. You might have consistent junk, and then you might have additional classes. So you would always specify more. So on a rule of thumb, we do anywhere between 50 and 10,000 particles per class. Why? Because you might have 1,000 particle data set or a 1,000,000 particle data set. So it really depends on similarity. So if you don't know, then this number of classes is something that can be optimized.
So
You might
multiple
end up running multiple times. You'll see in CrowdSpark it'll have a criteria to give you what it thinks would be an ideal number of classes. So if you specify more than it needs, it'll say like, I think some of these are actually similar, so you need less. You could always specify more, but you don't have to. That's a difference. Right? And it's a matter of efficiency, because the more classes you have, the slower the processing will be. The more particles you have, the slower the processing will be, but you might need particles, so you might not have a choice. So I'm just going to go over some results. I'm going to pop into. I wonder how far I've gotten here. Only 8 angstroms so far. Okay, so I'm going to pop into another area. I'm going to pop into the folder that's already been run. I'm going to go over some of the outputs that you can expect. And then we're going to change over to, we'll take a short break and then we'll change over to Kraus-Spark. But this is to give you a primer of certain things that you can do. So in this case, the workflow, so this is also where annotating certain things may be helpful. You can actually add more than just a job alias. You can add notes, etc. But in this case, I did an extraction run. The native box size was 288, but then I binned by 244 pixels. In this case, I was very explicit. Reline will tell you the rescaled pixel size. In this case, it's a 1.7-ish. There's a little bit shy of 60,000 particles from 443 micrographs. Note that they're closer to 500 in the folder. Not all the micrographs had box files to use. Then I did a 2D classification, and there's 2 different 2D classification runs. The difference between these 2 runs is whether I ignored the first CTF, or ignored CTF corrections to the first peak, or I didn't. And in your tutorial, you'll see the relative outputs, but something that can happen in 2D classification is class collapse. And that may be something that you don't mind or something that you do care about, in the sense that if you have particles with high symmetry, what could happen is that many classes merge into one class. And that may be useful to know. So for example, in this case, though I specified several classes, you can see really everything collapsed into only a couple of main classes. Or if you don't correct into the first CTF peak, then you can see that there's less class collapse, where there's a few of these classes that you may see that could be merged together. And some people may feel that one versus the other might be helpful for analysis, or in a sense, sorting out their data.
So which one is which one? Left is no, right is yes?
This is no, this is yes. It depends. What's that? No, yes. Okay.
My yes is this random?
So this is.
What's yes?
This is ignoring the first CTF peak, and
Yeah,
this
yeah,
is
ignore
with
it.
the
Yeah, yes, to ignore.
Yes.
But you can see a lot of detail. Okay. So again, something peculiar is if I just displayed, which I should have kept it on, maybe I'll keep it on. Let's see. So if you're just using a display, I just want to underscore that, okay, so if I'm using a display, I can say like, oh, okay, I like a particular class or not. Save subset classes will be grayed out, because this is just something for display, right? If I want to actually select these 2 classes and save them, I don't use a display. I'll have to go explicitly into the subset selection job and select a particular particle stack or model star file, and then I can then save it. So in this case, I selected and saved 8 classes, which were, roughly half. I also ran initial model, and in this case, I only ran one, I believe. Right, one class. You could specify more than one class. And in the tutorial, I showed you, it uses stochastic gradient descent, one way of energy optimization. But I showed you the different iterations as it started out as a sphere, and then eventually went along the way and found a shape. So here's what it is. In this particular case, I did impose symmetry. So I think these are every 50 or so, or 20, 25 or so. So then we can show you the evolution of, it starts, it seeds with a sphere and then tries to generate an initial model, and towards the end it's actually quite a reasonable initial model. The reason why I'm showing you that is that if I displayed it here, let's say I displayed the model, as I mentioned, what it is, it's 2D slices through a 3D projection, and some people may be used to seeing this view, some people may not, but these are actually 2D slices through a 3D body, right? And you can see even in this initial model, you can see secondary structure, and you can see the symmetry imposed. So a better thing to do, every time you generate anything in 3D, I would recommend viewing in a 3D viewer. Any output, I would just recommend viewing, because despite you asking the program to do something, it may not, it'll do what you tell it to. It may not give you an interpretable result just because of certain parameters. So something that towards the end of the workshop, what I hope you would have time to do is start playing and change certain parameters and see how that impacts. Because it's useful to know on a test data set when you have a known result, because you may not know, like, oh, okay, what happens if I make the diameter really tight or not for a mask, right? Like, I know my particle should be X diameter. Now, what if I make it, just at tight, larger, smaller? Masks, if you have a hard edge for your mask, you might introduce artifacts during that alignment. Okay. Afterwards, I did a 3D initial model, or actually a 3D classification using the initial model, and I chose 3 classes. If you just show the model.start, you'll see the 3 different classes come out. And you can use classification as additional criteria to try to assist you with some sorting. So here's you can already tell that there's different resolutions, but if you display and then you show the metadata, you can see that there's certain statistics that it's binned heavily, so there's an estimated resolution, and in terms of how accurate it is with rotations and translations, and you can compare and contrast. You can use some of these statistics to compare and contrast whether one model is better or not. But the best thing to do would be to download if you have a 3D object and then view it in 3D. After classification, I then selected one particular class and I ran a 3D refinement job. And there are many different outputs where you'll get, what it'll do is something called gold standard, in the sense that it'll split your data set in half, and it'll compare 2 half maps to each other to determine a similarity. And in this case, these 2 half maps were similar out to 3.7 angstroms. This is actually unsharpened, so one way of looking at a map would be to do sharpening, and when you have time, you can create a mask using mask create if you want to create masks, and you can then sharpen it using the MTF file for the K2 that's in your folder. So these are in your tutorial, there are other additional tasks you can run. So by running sharpening, you can see the final resolution has increased, and if you actually look at this particular 3D model, you'll gain greater detail. So all in all, given this particular data set, this entire run took, well, back in the day when we were running Reliant 2, it took a half a day. Reliant 3 might be a little bit faster and depending on your GPUs, but this was the particular workflow that we used, and this is assuming the binned data set for GDH. So this is quite reasonable in the sense that okay, we might not be working with an entire data set, and we might also do very severe particle sorting. But this would give you a good indication whether or not you want to work with this data set some more. So you can say like, okay, with doing this crude workflow, I have 3.4 angstroms, and then there are other things you can do. You can reprocess it. Let's say you can unbin it. Well, unbin I already showed you gets down to 3.1, and there are other features you can run. But the advantage is that if you do some preliminary analysis, it only takes you a few hours on the data set, then you have some quality estimation on this data set. And now what happens if you're in a research program and you're in a regime where you have multiple data sets, dozens of data sets, this can assist you with prioritizing and giving you indications where, yes, I might have a 3.4 angstrom resolution map, but okay, I'm actually after a ligand, or I'm after a component that's binding there and it's not there. And you can say, well, is it really not there, or is it just very flexible? But again, these are now additional questions you can ask and more informative questions on your data set that you may not answer if you're just looking in 2D. So it behooves you to parse your data, to be very efficient in analyzing your data. It doesn't take too much time, and it will help you be in a better position for answering your scientific questions. So, and you can see, again, this was accelerated because we didn't use so many iterations. So this shows you where you can really cut down on the number of iterations and have some feedback, right? And this is not to say that this is going to be your final reconstruction, but this is quite a respectable reconstruction that you can make use of to really start. You can do initial model, like PDB docking. If you already have a model, you can see how well this compares and contrasts to certain things. Right.
For example, if you have a data set with a large number of particles, would you just analyze the portion of that?
Well, for initial assessment, I would analyze a portion. At the end, your final processing, you would need everything.
Mm-hmm.
And something that you can do in Reliant. So let's say I worked with a bin data set and I did some particle curation and I just had a selection. I can actually go back and extract and say, I can re-extract the star file, and I can then bin it less. So one thing is, if you have, let's say, that million particle data set, initially work with it binned. Try to do as much curation as you can, and then ideally now you're not at hundreds of millions, but maybe hundreds of thousands of particles that you can unbin, and then it'll be a little bit easier. So there's certain efficiencies that you can take to handle that. The reason being is that you may not have unlimited computation. So yes, Amazon is on demand and you can scale. You might have a cluster. However, you might collect a data set that, okay, let's say you're working on a very large virus with something bound to it, and you need a 1,000 pixel box size, and you have 100 million particles. Most people would run out of computation really fast if you collected in super res and worked with everything unbinned. You'll just tax out all the computation. Like, even if you get more computation, you still run out of it. You might be lucky in the sense that you're working on, a more modest protein, but you can still quite easily collect more data than you may need to process, and you need some criteria to work through it. So be as efficient as you can, and you may also, if you unfortunately have to work with your full data set unbinned, then just note that what you're giving up may be time. So you may be able to process through it unbinned, but it'll just take longer. It really depends on what you need to get from your data, and sometimes it is not so trivial to say that, okay,
can I see a distinctive feature in a bin state? Can I see it even in 3D classes? Maybe not. You might need to go all the way to refinement and do some more of these more subtle techniques to get additional information for you to sort out. So why I'm saying that is that that's where I'm seeing most of our users. There was a user in Appion Part 1 that not a problem. They can get three angstrom reconstructions from their data set. Not informative. It's been solved by X-ray crystallography 20 years ago. So that's no value add. So they're in a regime where they have to solve multiple reconstructions from a single sample to really push science forward.
To see different confirmations.
They need different confirmations. They need ligands. They need particular transitional states. Some field, in that particular person's field, it's actually really easy to, it's not trivial, but it's very straightforward to get 6 3 angstrom maps from the same grid. So he was in a particular field where, yeah, this becomes very important, because just because I get your 3 angstrom reconstruction doesn't mean it really helps you. It's actually quite disheartening when you're like, oh, I have 12 data sets, all of them go to sub 3. None of them answer a scientific question that hasn't been answered already. So then what do you do? Well, hopefully you can design your experiment where it's not all or nothing, and that you're not after something that's only 1% or a fraction of a percent within your sample. Because you're really, now then you'll really have to push your data to really see that. That's very, it's very hard. That's a very hard position to be in. So hopefully you're working on novel proteins that you have worked out biochemistry, and it won't be so severe in terms of a research project. Okay, so you can still eat pizza, but for the sake of time, we're going to take a very, very short break, but we're going to start converting over into CrowdSpark. Is CrowdSpark spun up yet, or do I spin it up?
You have to.
I have to spin it up. Okay, so this is so something that we're working on here is on demand. We can make use of certain. Is that website?
I have sent you the Slack.
Through Slack.
Message.
So this is not released yet, but through NCCAT, we have noticed that a lot of our users don't have sufficient computational resources in their home institution. So therefore, so that's from yesterday, the
link.
This one?
This one?
The top one?
Yeah.
Okay. So what Swapnil from our team has been working on is that you can spin up AWS instances on demand in an easier fashion. So we don't look at this. This is coming soon. So there's a lot of things that we're trying to spin out. But what we're really focused on is we made use of Leginon during Appion Part 1. We made use of Relion earlier, and in that case, Swapnil did this for you. And right now, we're working on CrowdSpark, which is the next segment. If you want to take a picture, you might want to go to the back and see, like, there's actually people doing like this in this real time. But we're going to do something in the sense that what users eventually will have the capability of doing is that they can go and on demand just say, I want an Amazon instance, I want computation, and then I can spin it up. And since it's on demand, it does charge you per unit of time, you can stop it and start it and still keep your data archived there. So this is what we've been rolling out for workshops, but now you get to see a little bit more of what's up and coming. So in the sense that what I want to do is, it's as easy as you go to this website and you say, I want to launch CrowdSpark. And it does take up some time. So what's happening in the back end, which you don't see, is that it's, going to AWS, like authenticating a lot of things, spinning up an instance, getting the data you want in there, making sure it has an environment of all the
computation that you need. And to assist you with the tutorial, what we want you to do again is we have the tutorial on Redmine. So along with that issue, so if you haven't gotten that PDF, what I will suggest that if you go to feature 7198, given all of you have registered for the Appion forums, you should have access to this. Again, if you have issues with computation, this is also the forums where you would go to submit tickets, as it were. So then, in that case, we have the CrowdSpark tutorial guide, and then you can go and download that, and it will encompass a lot of what we want to do. So, by a click of a button, basically what I have is I have the ability to start CrowdSpark. For this particular workshop, we actually only have one CrowdSpark license and we'll be using ours. So we're all going to be sharing the same CrowdSpark server. In this case, unlike for Reliant, where each of you had your separate instances, those will still work even in the background. We're all going to be sharing one instance, but in this case, we're going to go and spend a little bit more money and get more GPUs, and that will assist you. And since we're working in groups, hopefully it won't be too much of a lag for you to actually submit jobs and see outputs. So if you go to your CrowdSpark tutorial, is this static link is what we want to use? Yeah. Okay, so I spun it up and I can go into CrowdSpark and you know, if I just go, I can open up CrowdSpark, I can open up and begin CrowdSpark here, and then good to go. I would recommend that you go to the Redmine issue. That's the whole part. We try not to waste paper. So that's the intention why we only printed so few copies. But I believe the right IP is in the tutorial that that if you go to in your web browser, that particular IP, let me just double check to make sure it matches. Yes, it does match. Then you'll be able to go into CrowdSpark. So for me, I booted up the instance and I started it up. But since it's already started, you don't have to do that. You can just go straight into the CrowdSpark instance. So the tutorials that are online has a lot more information than I'm going over, but I'm just going to go over the basics to give you your bearings. And again, I want to give you license in an environment to just try to make use of these programs. And then after you get through some of the basic workflow, we can go into more details of certain offerings within each program. So if you haven't gotten in there, we'll go around. But first, let's orient you into CrowdSpark. So when you first go into CrowdSpark, you get this main page. In this case, we're running CrowdSpark 2.11. If you hit projects, there are no projects. So what I want you to do is create a project. And someone did it appropriately already. Someone created Appion 2 Group 6. I'm gonna be Group 0. But create your own project with your relative group. I misspelled. And I forgot it too. Okay. And where do you want to save that? Well, you want to save that into our. So something we'll have to do is be a little bit patient. Because unfortunately, since we're all in the same web browser, we may, and we're using the same instance, as we're doing it, we might override each other's paths. So for the first thing we do, let's see if we can get everyone to create a new project in EFS projects in the relative group. And so that's great. We have most of the groups going. But do be a little bit patient, so we should have 5 groups. Is group 2 okay? There we go. There we go, everyone's there. So then go into your representative group, and then we're going to create a workspace. So this is how CrowdSpark is organized. You have a project, and then you have a particular workspace. And then you can title it as you wish. Okay. So to orient you, ideally that you go into your particular group and you go in and create your own particular workspace. So this is going to help us because everyone's going to start submitting jobs. They may or may not run into trouble, but that'll allow me to understand which group is having trouble and how far each group has gotten. Again, along with the Reliant instance, this instance will be kept for the remainder of the day, and towards the end of the day, during when we go break for the picnic, a little bit after that, if you want to work, you can still work, but then by the end of the day, we'll stop all these instances. So you have some time to play and understand how each program works. Okay, so you can basically follow the tutorial, but how I want to orient you is make sure you work in your particular project, your particular group. If you hit Job Builder, you'll see, very similar to Reliant, a set of jobs that you can run. Certain things that we're going to do is we're going to assume you've done Appion Part 1, basically the pre-processing, and even still, we're going to say that you've already extracted particles, because that's what we just did, right? So now this is going to be good because you can get some comparison of the different outputs of running very similar jobs. So in this case, we're going to import a particle stack, and the particle stack we're going to go to is in this particular location, and in this case, the GDH bin 2 would be the 144 pixel clip. We can select that and import that particle stack. So this is how you would do things, in the sense that in these metadata path, you would select the particular star file. You can skip all this because in our particular star file, all these parameters are located. So you don't necessarily have to add something else. In this particular case, we're working on, is it the workshop node? Workshop node. So when you submit the queue, make sure we're working in the workshop node and create it. And then, and so when you're running jobs, you'll see it go along, and this is what happens. And this is quite fast in the sense of importing. So let's say you have a particular job that's running, you can select it and hit spacebar, this window will pop up, right? If you hit, and you are creating a job, and let's say, I want to do a 2D classification job, and I want to get particles. This is very like click and drag. So if I select this, hit spacebar, I see particles, I want these particles here, and for efficiency, I might not do all 50 classes, I might do a lot fewer. And then if I accidentally hit cancel, like oops, what happened? I want to build that job. I don't want to keep on doing that. You can either select the job that's building again and go here, but if you're somewhere else and you cancel, you can always hit B. Let's say you came out here and you want to go back to this job, you want to build it. I mean, you can click on it, but you can also hit B and you get back into the builder area. And then don't forget when you're starting to run, you hit this node, the workshop node, to run your jobs, and it'll launch and it'll run. And things like that, in the sense that you can also queue up certain jobs to proceed forward. Let's say I want to do 2D classes to select. Even though this job hasn't finished, I can drag over my particles and class averages and queue up this job to run, such that when this 2D classification job runs and finishes, then this select 2D will run. So this is to get you oriented in this environment and have you start. So the idea is the tutorial is there. The main thing is this should be a pretty intuitive interface. The idea is we're starting from particle stack that has already been extracted with CTF information in there, so we can skip a lot of this. If you go through and finish the tutorial really quickly, we do have the micrographs
from either the Appion Part 1 workshop or certain micrographs from here. And what you can do is this workflow. One note is if you want to do CTF, these features don't particularly work in our instance. You would have to do patch CTF estimation if you want to do CTF on a micrograph. But given that we're starting with particles, don't do CTF on that. This is only if you load a different data set. Okay. There's certain things like, let's say you create a job, you know, you can always curate it, you can delete it, you can add a description, you can, you know, annotate it. If let's say you have a queued job and you don't want it, or you queued a job and it's running that you added a parameter that you don't want, you can always kill the job, clear the job, and then go back into the builder and update a parameter. Meaning if you just went on autopilot and you accidentally created certain parameters, and then but you notice that I actually want to change certain things. Let's say GDH has symmetry and you just forgot to add symmetry, or maybe you don't want to add symmetry and just process at C1, then that's how you can do that. Something that you notice that in here, as things are running, it will give you a lot of feedback in this log, and then as jobs are running within this window, you'll see different outputs come out. Okay, so working your various instances or various project folders. Try not to queue up too many jobs, so we can see we have at least 16 GPUs, and okay, well, we're not quite using all of them, but the main thing is make sure you make use of the workshop node, because that's what we're using for this particular instance. If you accidentally default to any of these two lanes, there are no resources, meaning there's no GPUs or CPUs really that you can make use of. Okay, so that's the resource manager, so you can see what resources are being used. And then one advantage is that we can, we have access to each group, so we can see where people are getting stuck. Right, so again, I'll be working in group 0, and you can already see that there's certain feedback where this is only iteration 1, but you can see feedback as it goes. Now it's on iteration 2. And very similar to what Reliant did when you use fast subsets, you can see that this is only using a subset of images. So every iteration it uses a larger and larger subset, and right, it's not using the full particle stack. Right now, this iteration has only 9,000 particles. How many particles did I start off with? Well, you can see in this particle stack, well, in this case, this is a little bit smaller. It's the 16,000. So this is this particular particle stack is assuming the particle stack from that refinement example I showed you from Reliant. But even in the few iterations, you can start to see, you know, a lot of detail. And the display is slightly different than Reliant, but then you can see how many particles, you can see some resolution, you can see some statistics. And even after 4 iterations, you can really see quite a bit of detail. And there's a lot of certain things you can see, like effective number of classes. Remember, this was the question brought up, how many classes should I specify? Some people specify 1 class, some people specify multiple classes. In this case, right now, it's running that, I mean, if you only had, like, there might only be a certain number of classes required to account for most of the data here. You can already see that it's really falling into only a few poses, but you can see here that if I only had like this many number of classes, it counts for most of the data. So there's different feedback in each of these programs which can help you characterize more of the data set. But the idea is that in this case for CrowdSpark, given the computational resources we have, you can even do ab initio modeling. So not only just import a particle stack, do some 2D classes, you can select it, and then you can also do ab initio reconstruction. And most of the time for ab initio reconstruction, people use C1 symmetry, but you can see what happens if you do add symmetry. D-symmetries are a little bit tricky because you can have C1, C3, or D3, right? You can choose what type of symmetries you want to process that in. And you may view one might be better for your criteria for sorting out data. But the idea is that you can see here that a lot of the interface is, you know, point and click, and then you can always have
you can always feed forward certain inputs that haven't been even generated yet to queue up jobs. Right? So like I'm even queuing up ab initio. Don't forget again to hit the workshop even before this is done. So these are queued and just waiting for this to run. When will this finish? By default, what will happen is that this needs about 20 iterations to run before it says the 2D classification is complete. Right. Okay, so want to get you used to the interface, you can start poking around. CrowdSpark is a very friendly web interface. The tutorial has a standard workflow that we're going to have you do, which is very similar to Reline, which is 2D classification, ab initio model generation, 3D classification. In this sense, you'll do heterogeneous refinement, and then you can do homogeneous refinement for that 3D refinement. And in case you haven't gotten here, I believe everyone has, but this is the IP, and this is a static IP that will be open for the remaining part of the day. So you can see that if you have any questions, the ability that we have is that we can start seeing the various groups runs, and then if need be, we can pop in and monitor and see where people are and where people get stuck. But the main thing is that what you may find is that CrowdSpark is fast such that you may be able to try doing a run in more than one way, meaning you might be able to try different parameters. So please do go around, and we'll go around and see where people get stuck. But one thing that you might find useful is that you can see this feedback. Oh, I see some people's jobs failed, and that's a good thing. That we'll walk around and we'll try to resolve any issues as we find them. But it's already amazing. You can see the level of detail. So what a lot of people do like to see is the secondary structure detail in the class averages to help them with the criteria of is this a good reconstruction or not. Another advantage of the web interface is you can come here near this and you can download certain of the outputs. And this will become more useful, and why we ask you to also install Chimera, because you'll also be able to download models. Within the data set, in case you do decide to skip ab initio, but ab initio runs really quickly, you can import other things. We just imported a particle stack. You can import volumes and other things like that. So let's see, where is that? Import 3D volumes. We actually do have a 3D volume in this workshop data set. For example, these 3D volumes. So you can actually work with not just the bin data set, you can work with the unbin data set if you wish. Every time you run, don't forget to use the workshop node, and this is importing a volume. So this is just to show you how CrowdSpark views volumes. It shows you in 3 orthogonal slices. But why I'm showing you this is that in here you can actually download a map. This goes straight into your downloads folder, and then you can view it. So that's also why we asked you to make use of Chimera. So if you don't have Chimera installed, you can, we will walk around and try to assist you. So now that you're in the web interface, this is the 3D model that you were working with. This is the same one that we had you use in the Reliant tutorial. Right. So this is also why we asked you to low pass filter it, because this is already a pretty good initial model. So I'm just gonna do certain things just to make sure to see how long certain things take. Okay, so we'll walk around and see where people get stuck.
The way you were changing the pattern, it seems like everywhere
I'm just very familiar with the interface here.
Running, so you can queue up jobs before they finish, so they just go on to the next thing. I guess the selecting like the 2D class icon is a little bit. You can do that as well.
So for example, that ab initio run, I have 3 classes. I could actually set up homogeneous requirement on each of those classes before it finishes. When ab initio finishes, it'll start 3 independent, or 1, or however many I set for refinement.
Okay. Those classes will evolve as the iterations progress?
Well, the main thing is it'll wait for the previous job to finish, and then forward that information. If you run, say, Crosspark Live, yes, you will do that, means streaming. As you push in more, it'll evolve. But this is waiting for one task to finish before moving on to the next.
Import another database.
Which one? Databuds?
Oh, okay. You have already.
So we are not looking for articles. So this is a metabug, right?
Yes. So if you're importing the star file, all you need is the star file because if the star file and MRC stack are in the same directory, it will already know where the file path is. So all you need is the metadata path, and you can leave the particle data path blank.
So we don't need to specify.
You would specify the star file. So again, the reason being is the assumption is you've already done Appion part 1. We actually even have done the initial Reliant part. This is just springboarding into Crosspark.
So this is star file.
You can take the star file directly. You can take the binned or unbinned, doesn't matter.
Which is a particle stack. So now
So the result it opens the
For the new job.
going for a new
So
job,
each
it's
of those are
new jobs.
So this one is the first one,
So it says?
after you go to the particles up.
Declassification.
And then this
This
one,
one
you can also see that this one's highlighted blue, right? So now we're in it, and it's grabbing particles from the red ones. So that one's in red. And then this is also used in the green one over here. Because this one says completed, it can go through, and then it's
Oh.
So what we have to do is just wait until we have something.
Yeah, it's just
It's a material for a big surface.
Yeah.
I guess this couple are fine, but then the rest is.
Circular mask you want?
So we can create these drawbacks.
Then you can create.
You want to do it?
Yeah.
You can start right now. Yeah. We have a static IP. We spun up an Amazon instance. You can just join in. You have the tutorial.
No, it says
Sort of missed the first part.
There's a different view compared to
Yeah.
real kind of approximation. So in real life they were able to get features somehow faster initially.
but I can change it.
Authority, it's J1, so
That's
it
too
should
long.
be
Does anyone want more pizza, or can I give someone else pizza? More pizza? Pizza, pizza.
even
This
though
is
it's
Joe.
work
Just our original flavor, right?
Let's try
I don't think
job.
so. It's the right job to particle.
It's already
The
here.
original is job 1 particle, so it's different.
And job 2 is.
Saw that.
Yeah,
Yeah.
I think it is particles get selected and this is from average and the calculate, so it's different. Then it's already excludes some conflicts. So that's those that they
So we have 16 GPUs, but given that we're working in pairs, I think everyone would statistically have a GPU at all times to be crunching some data.
Did you stop your finish your TV class?
No, I let it complete. It's pretty fast. It only needed 20 iterations. Some people like this responsive feedback because as each iteration goes, you can see visually certain updates, right? And I've done multiple things at once. I've done ab initio as well as refinement, right? And it also gives you a shortcut. But if you go into each run, it gives you those orthogonal views, FSC, B-factor plot, also distribution of Euler angles or views. But even in ab initio, you can see the different models. And why is it so fast? You can see the count is pretty low. So very similar to Reliant where you use fast subsets. It's not using your full data set. It's using a subset, and each iteration it adds more and more particles. However, the issue with fast subsets is, let's say it chooses a non-random subset, or it statistically, unfortunately, it randomly chose things, but of the same view, then it will be misrepresented. So let's say you have like all views, but for some odd reason, the first 100 particles end up being the same exact view. You may have an issue unless, let's say in this case, we have symmetry that we can overcome certain things. But that's unusual. That'd be highly, I would buy a lottery ticket if that was the case. Because you'll be a very special regime.
Yeah, I think that we would have to.
So something you're noticing that, let's say Reliant has CPU modes, GPU nodes, CrowdSpark can run GPU. A lot of certain modern programs can make use of the CUDA cores and basically just the acceleration by having so many more possible computation on cards. something to make note of when you're working with particles, larger particles, the VRAM on your GPU matters, because if you have a really large box size, that's what matters. Like, what's your box size? Because that's a certain number of megabytes, and in your VRAM on your card, if you only have like 8 megabytes or 12 or whatever, like that, it will top out really quickly, because you have to copy. We're dealing with images, so you have to copy that images into the card to process, right? So that's something you have to make note of, and that could be the huge computational expense and purchasing expense. Hence why running Amazon On Demand, you can run different instances, different cards, and you can see, okay, it's really fast, but is it $10,000 fast? Is that, do I want to buy a $10,000 card? Maybe you do, maybe you have to, but at least you'll have a better appreciation for the difference between, let's say, a $2,000, $5,000, $10,000 card by running it. Another reason why we're trying to do this, so you get not only familiar with the program, but expectation of time frame for a job to complete. Because that might not, you can look at the specs on paper, but that might not correlate like with the feel of processing. Right, and in a very short period of time, I already have a 4-inch in Reconstruction here, right? And this is what run. Right. When the ab initio finishes, I'll start another refinement run with this ab initio model. But you can say, like, I bootstrap with an initial model. Am I worried about model bias? You can see that in here, I already low pass filtered my initial structure to 30 angstroms, in the sense that if I achieve resolution beyond that, well, it's not coming from my initial model. And so that's why I'm referring to certain programs automatically in default have certain settings that make it easier for you, but you should still know what it's doing so you have a better appreciation.
To make sure that you have the right box size, what do you look for?
So in this case, we already assumed that you extracted the particles with the right box size in Reliant. If not, then you would see that the box doesn't contain your full particles. So you might decide, well, I want a larger box size. In this case, in this example, you wouldn't be able to do that, but how you would normally do that is when you import movies and you do your particle picking, and then you do your extraction from micrographs, you would specify the box size, and you could always bin. So here, so then you would re-extract with a larger box, and you could always for your bin to make processing more efficient. But this is the same idea, like whether you're in Reliant or you're in CrossSpark, there's a job where you can specify your box size and whether or not you want to bin. But if you chose the wrong box size for some reason, you would have to go back and re-extract.
So then you essentially just go back
Right.
to Reliant and re-extract.
Or you can if you had micrographs and particle picks in CrossSpark, or you loaded it into CrossSpark, then you could re-extract here as well. Let's say you have too large of a box, there's only so much you can do. You can add a mask, but if it's exorbitantly large, like tenfold too large, yes, you definitely want to re-extract.
So
What
then-
does mask would do in that?
There are certain masks. You can have a tight mask or you have a circular mask. A circular mask would be, let's say in Reliant, the default was 200 angstroms. Or the main thing is, so you have your box size, but it applied a circular mask with a particular diameter. So it's not considering anything outside that, from the center beyond that mask. A tight mask would be shaped based upon, let's say, a volume. And that would require you to have a volume. And then in that case, it's not just a sphere, it's actually a mask that is based upon your 3D model. So meaning if I had a tight mask, a tight mask of this would not be a sphere. I mean, in this case it would be more triangular, in this case it would be more rectangular on this
Have a shape.
view. It would have a shape. And in here, in this case, in the refinement, it actually has created a tight mask where
it looks like this. Where this is sort of like more triangular and this is blocky with a couple lobes. So it's no longer a sphere mask. Mask actually has a shape. This could be good and bad because you're imposing a shape. Now it can also impose a shape that removes certain parts of your protein. That might be good. Let's say you have an antibody and you don't really care about the FC regions. You just care about the FAB part. You could have a dynamic mask that just chops that away. But let's say you're in a case where you're in a complex and just so happens the area of interest is a little bit floppy. CrossSpark's dynamic masking may actually mask away that area. And then it will give you a very nice core resolution, but you just don't have that region. So and this is what I'm reflective of. No matter what the program's doing, it's good to be aware of what it's trying to do, and it will do what you try to tell it to. Most of the defaults are pretty good, but it may not be exactly. So you can see, well actually after 2 iterations I'm already at the 2. So something that might be helpful is like I can actually, I can download this volume, and I can download this mask, and this might be a little bit more informative in showing you what has happened. That's too secure of a web browser. MRCs are dangerous. Again, too many windows. Here we go. So here's that shape mask. So that gives you a representation in 3D. So this is why I also want you to have Chimera, because what you now can do is not only have outputs. If you have a 3D output, you can now begin to look at the shape. So if you don't have Chimera installed, you can use another viewer, but Swapna and I will come around and try to assist you with that. But yeah, so you can see like this mask is more reflective of what you see here. That's the mask, and this is not a spherical mask; it's a shaped mask. I can toggle that off, and this is already the reconstruction that's coming out.
Now, see if your flexible part starts to disappear, what would you do?
Well, then you can choose a different mask, or you could rerun it, focusing refinement on a particular area. I mean, there's many things you can do. So you can say like, okay, well, in this case, I don't know if you may not have seen some of the raw micrographs, but the way that the particles work, there's this particle and there's another one of these over here. So this is actually from a neighboring particle. But let's say this is a region that I was interested in. Then something you can do is you can do focus classification by like masking certain areas out, looking at here. You can do signal subtraction, meaning subtracting the volume, like the densities of here, and leaving that here and looking at. Or you can do, let's say, classification where you initially have this alignment and then you classify, because what might happen is you might have heterogeneity in this area where you may have certain classes where you can tease out one conformation versus another. So it depends on what you're after in your data set. There are multiple approaches to try to focus on areas of dynamic behavior to see if you can just use some criteria to pull out defined states. If you have a situation, though, that you have an area and you have continuous conformation, that's hard, because continuous conformation would be, how many points do you have in a circle? Infinite. So you have an infinite number of conformations here, then you need an infinite amount of data, or you would have to arbitrarily say, okay, I will sacrifice resolution and arbitrarily bin this continuum, then bin this continuum, and then you would have some more information, but it won't necessarily be a high resolution. So again, this is the danger of using resolution as your only criteria, because you don't have a defined state. So in structural biology, especially if you're doing averaging, you need defined states. We don't handle continuous conformational change at all well, because that would in fact equate to infinite number of states, and if you're doing single particle, you need infinite number of data. All right, so the hope is that you have a regime where you have,
okay, you might have multiple conformations, but they're defined states. So it might be something called semantics, but it really matters, because if something is truly floppy, let's say a loop, completely disordered, completely random, then you may not be able to just use standard structural biology approaches to look at it unless you artificially lock it in, which may be informative, may not be. And so that's why no modality is alone, where structural biology can be used in concert, in complementary. So you can make use of all different modalities and combine it. But you can see, even after a couple iterations, yeah, you can see quite a bit of detail. And this is sort of the advantage of the data sets we're giving you in that what we don't want you to be is artificially stuck in a particular step. So let's say, okay, I want to do ab initio reconstruction, but I'm failing at 2D classification. Well, this data set is robust enough that you could always jump to the next step without doing the previous one. But the hope would be then you could figure out what's tripping you up, and then you can use this environment to go back, re-optimize parameters, see what's under the hood, and better understand what happens if I do change some of these parameters. How much am I affecting? Because you might say defaults are great. You might say, I want to actually change some of these. What magnitude do you change that? You won't know until you start playing around. And so a test set also is helpful because it gives you, we have a defined answer. And you can see in your tutorial there's some additional things you can do. So if you're able to get 3D reconstruction, something they can say, is this the right hand? Because we are projection images, there's no guarantee that all your helices are the right hand. I mean, if you can see helices, you can probably just outright look at it. But there's a chance that it parses your data and you get the wrong hand. So given that I told you this GDH, you can go and download a PDB, and if you have Chimera, you can open it up and match to see, does it match? Or maybe the conformation, the reconstruction we have is a different state. So then that might be different from another PDB or EMDB of this molecule in the database. So let's see. Do we have another? Let's see. What? If you have moved along, we have a couple of data sets. We have an Empire data set with aligned sums, and then we have also a movie stat. So if you finish this tutorial, there are other data sets that you want to go from micrographs forward, you can. If you do use the Empire data set is, I think it's this one. Right. The Empire data set that we're using is this particular data set. It's the T20S proteasome. And these are the files that we're using. So let's say you are going to be practicing, and you can say, okay, great, I've downloaded a test data set. You may not have all the information here necessarily to do processing, because there's certain information that we took for granted because you're working on a Legend on Appion. We already fed all the information for you. You don't have to worry about that. But if you're collecting at another center, or you're collecting, or you're downloading data, some of this information might not, may or may not be in here. Okay, is it in here? So something that you may have to do would be go to the original publication and find some of these statistics. Because what's the high tension? What's the acceleration voltage? What's that? Well, fortunately, Leginon already gave you a star file with all of that. But let's say you don't have that, then you may have to go in and view it. So let's see. So in this case, if you go to the Empire data set and you were to use these, it's the aligned sum.
Data collection. It was a kV, 300 kV. Full dose, 53 electrons. Here's your pixel size. And given that it's collected on Titan Krios, the CS is 2.7. Now you know why we like Leginon, and this gets a little bit more confusing because yes, someone published some data, and great, now I have their data. You still need more information than just the raw micrographs. And this is just giving you a clear example of why certain pipelines are fine. It's just that you need to do more or less bookkeeping depending on which workflow you do. So if you do decide that, let's say you've gone through this test tutorial, GDH, yeah, you got, it's already in the 3s, you're ready to go, and you want to, let's say, use the Empire dataset, this Empire dataset. These are aligned sums. Pixel size, 0.6575. CS, 2.7. Total dose is 53. What other information do you need? And this is a 300 kV high tension. You can always get that from the paper. But I would first recommend that you try the GDH just to make sure that you understand all these parameters and get that to work. But and we'll give you some more time. In about half an hour, I'm going to go over a review of certain outputs, very similar to Relion, and then we'll just give you more time to just try out both programs. So again, I would say that for the next half an hour, focus on Crossbar. After that, we'll go over a review, and then you have both instances open, so you can bounce back and forth to play in each environment and see which environment you feel that you're more comfortable with and get more exposure to. Okay, so you have data and you have additional data sets to work with, and the idea is not just run a job once, try running it again and try different parameters, because that might be informative to give you a better idea of, let's say I don't have such a good protein, let's say I have a trickier protein. Does changing a particular parameter impact the particular processing job or run? And this is the perfect data set to work on that. And if you run out of all of that, towards the end of your tutorial, you have a couple additional tasks that you may try that are recommended. It's topped out.
Don't know what did we change the parameters or we use the same parameters?
No, you changed to C123. That's it. Which one? I changed C123 to D3. That's it.
This is
It's D3.
D3?
Yep.
class we don't want to use, so we just want
One will work.
My protein would not have any symmetry.
You want 3? It should matter this one?
No, you can do one.
1 to 4, yeah.
Clear it and try running again first. Clear job and clear it.
This is VC1, right?
And Q job on default.
So it's kind of like
Yeah, with the right processing lane, yeah.
I see. So you have like heterogeneous, right? To join up to part. and then you choose one of these, and do homogeneous on this one, and then do the second one, and
Yes.
see do you have.
So the selected
like,
classes
yeah,
from the subset selection.
Yeah, it's kind of
No,
Yeah.
so then
Define
what
it,
it,
define
well,
it.
no, input it defined means it grabbed it, right?
Somehow
It must have been able to find the subset selection because it grabbed particles.
Yeah,
Class
so
zero
we just
particles
selected
must
some
be-
classes which are good and use those classes as a tool. We removed some of those.
Okay, well, let's look at the inputs then.
Look at the inputs. See, this is the particle selected, J6 particle selected.
Let's look at J6 then.
You want to look at this? Why is it 2? Okay.
Yeah, let's look at J6 first.
That's J6.
It's a funny thing, you have to select.
So we use this as the selected particles as the input for.
Yeah, should be.
And just drag this and to try again.
Mhm.
Yeah.
This one.
No, the top one.
Particle.
Yeah. And what are the other? This one.
Run
is-
this first and see if we come into error, and then you can always
Like
kill
default
it.
one?
Yeah, just run
Let's
default
see
first,
then. Okay.
and then we'll see if we have another error. And if we don't, then we can run again with.
assume we're
Move it in time for this and that.
I don't think so. We just need to find.
Yeah, it's working this one.
It's not really.
See one?
But what has symmetry got to do with working or not working?
Sixfold.
Sorry?
6 times more asymmetric unit.
6.
So what's the card? What's the GPU that we're using?
Output. So probably it would.
No, meaning in the Amazon instance, what's the GPU?
It's like K80, I guess.
Meaning you can exceed the processing capability. So we have cards, but we don't have.
But I saw
I think they're pretty good, but
import
GPUs eventually run out of memory. Yeah.
So it's one of the areas.
But that's reality because let's say you bought a workstation,
Yeah, that's true.
then you would be, then GPUs are horrible for you because then you need CPUs.
K80 GPUs.
What's the VRAM on?
Combined 192. So divided by 60. Mm-hmm. 12 GB, I guess.
Well, that should be enough.
But I don't know why is it replicating particles with symmetry in it. That is just imposing symmetry using same
But I actually don't know.
I'm running this with C3 now. Can't handle symmetry. It doesn't even take C3. C1 it is for you.
But if you're working with big particles, you have to apply symmetry.
Yeah, or if you want to make sure
We should move it much faster. Something more in icosaedral symmetry.
You want I.
What?
You want I, don't you?
Yeah. So that means it's going to replicate the particle that by the number of
So then you would need to
Symmetry
you need to
operations.
spend more money on. Yeah.
Really?
Or you make your box smaller.
Has depends on particle size.
Your pixel size would be larger. Then you would have to use CPUs at the end. It's an actual limit. That's what I was mentioning. It's a real limitation.
So we've had to do that on our system.
Yeah. right? Because you might see the cast.
We just wanted to make sure we understand. So we run into the change or long and which is initial, and the way that then we do the heterogeneous requirement, and then there will two like two combination or more, and we wall the combination, the volume and the mass from the wall to run the machine.
Right.
That's
Right, but if the heterogeneous, if they're all the same, then you can actually use, you can
Combine.
combine. Yeah.
But it would, okay. And here, since it take a long time, I saw here you have already made a model.
Yeah, so if you want to skip ab initio, then we already have a model that you can implement.
But they have to cancel out, right?
You don't need that. We don't have to. We can just wait. But we can run it first.
If you see three, or you see one.
Because now, so I should use like a.
Well, let's finish with the bread.
Import volume.
That's 3 times as much data.
So let's teach our approach.
Maybe we can give you a personal lecture on
And that's the lesson.
Job order.
That's like 4 or 5 days.
Would you know what they're saying?
But what's the part?
Seem sure if she
I've done and then never got that back.
It's gonna be an MRC.
You can know it somehow, you can do it.
Any of the top two.
You don't have to be told if you are electrical.
And then you just queue that up. Don't forget to select the right processing lane.
Okay.
That's just a peculiarity of how we're running the instance. Processing lane.
So the tool is only for gas.
That's gonna be fun.
Yeah, almost there.
So why don't we tell you?
Okay. We already.
Why don't you take this in front of them? Maybe this will make things up. What did he say? Did he do it for?
These I think they're the projections. Yeah. So this is from the 3-4 review, 3-4 Nexus. It looks like it, I'm not sure. Probably this is from the 2-4.
Then it'll be based, so here the setting is based on, assume we run the heterogeneous. That's for this one. I assume they were, I assume they already do some scoring, so to choose it as part of the.
What if we just choose the original data set, original protocol?
guess we could do that. Just see what's going on. It definitely works, but I guess it's not the best
Optimal.
choice.
Mm-hmm.
So let me explain it. So we import volume, but for the particles, are we gonna use the original particle? So here
You can
also
decide-
use the
It's up to you. You can do either.
Okay.
So we can choose either this one or that one also.
So
Yes.
both of them should work.
They will work, but if you went to the trouble to select a subset, then you would most likely want to use that.
Okay.
So we should choose this one.
Okay.
It's Empire directory. It says Empire. So you have to go in the EFS. Go up.
Yes,
Yes, exactly.
it's already.
That is the Empire. That's the yes, correct. But it's already gone through motion correction.
The thing about this one is you can always choose there and set up the workflow and the run and the data is at the yes, it's definitely okay. Probably should have put this through. Yes, I see.
C1 it is for this instance. We'll have to get better GPUs for you if you want to.
No, probably for refinement, I'll just give you three. It should work with for refinements.
Right. Well, that's what I'm using.
Because I don't know if I have an issue. Is it replicating the particles by
No, I don't know. I don't know. Let's see. I would have to go into the documentation how it's doing that.
I was under the impression that it would use same number of particles to enforce this symmetry.
Who knows? You never know. It's just because conceptually that's how it's done doesn't mean that's how it's implemented.
Yeah, probably it's replicating it by the symmetry.
Because by adding symmetry, it uses up different RAM. VRAM must be. Otherwise, why are we running into memory issues? Yeah. I don't know. I would have to look at the. There's no easy way to see the
I mean,
dimensions.
this has a very good interface.
Minutes to the wrong.
We can go into Empire. This uses the 42 gigabyte version.
Yeah.
I would download that. Meaning in Empire would annotate the pixel size. And so if it's super res, then it's if it's 7,000, we know it's native. If it's 3,000, we know it's not.
Yeah,
know what's
they
in
have
Empire
over
is
CSS, it's stable for the web app.
That's the
This is
pixels.
like a web application.
But you're saying
That's
that.
No, we have to go to Empire because we downloaded the.
Oh, you got the
source, right?
Empire
So
corrected.
Yes.
hardly anyone
So
pay
let's
attention
see.
to all the styling it.
Yeah.
They only care about the algorithms. But this,
So it's the 42 gigabyte version.
for academic.
It's 10
For academic,
025.
they're providing it for free for us. It's free 24 hours from a city company or biotech company.
Wow.
Need to pay.
Hopefully it's
$50
not.
$50,000 for one license.
So look at the different downloads, not this download, look at the other, this download. Yes, it is, because it's set to them both. They're both, no bidding, no bidding on that.
They would.
They would, that's
If
the
there's
same
an open source
thing.
thing available, then fine.
I kind of
They won't buy such licenses if they're expensive. But people sometimes do, even
So,
the non-profits, they
one
do
are different
buy the
slices
Google
of the view,
license.
one is the mask, this
Even
is,
Google's license cost you around
FSC
$1,000.
using the two half maps, and then
The
this
data
is
science.
filtered applying, that final tight mask.
Sorry.
So then that's why
Nothing is
there
free in the
are
market.
two versions of that, so that was what was used as refinement, and this is.
No, I mean you can
tighter
data,
mask.
transfer data
Go
using
down,
one
yeah.
line like the
And then
normal
this is the B
SEMC
factor
and all
used
that stuff.
82, so it uses a linear plot to plot that, we keep
Yeah,
on going
so-
down.
Yeah.
With the B factor, so it's like a negative, so it's, that's what it used for sharpening.
No, I thought you were asking about
But what-
only the data transfer,
like,
but not the storage.
what
It
was the number?
auto-calculated.
It's auto calculated.
It auto-calculated by fitting that line, and if the slope is
Okay,
82.
so, okay, I see this is more like a slope and
So, people use anywhere from, like, 50s and 100s are really good, thousands are absurd.
which means you convert too quickly or
Well, then,
is there something wrong? You shouldn't
well,
convert.
then that's what you think of temperature drive, that means your data set, there's not too much similarity. And if there's more and more heterogeneity, you'll probably see that out.
What's a log app mean?
I would have to look at the, look how it's plotting it, 1/d.
Yes, this is, okay, so
Reliant also has a plot of that. If you keep on going down,
This
the
is
noise
the-
model, I don't really look at that, keep on going down. And then this would be a representation of angular coverage, direction distribution. So, so if you have preferred orientation, it will be localized into one area.
okay, so this is 1, 2.
Well,
more
you
like
also
a
are
4
applying
class.
symmetry, so,
Oh, I
so
see.
then you make up for,
So it's after
if you only have two views, if you have them on the right symmetry axis, actually you don't care, because in this case it would cover everything that you would need. But if, let's say, you cannot apply symmetry and you have C1 and you only had a couple of views, then the map might be stretched in a few directions because you're overpopulating information. You don't have full angular coverage.
Okay.
You may not.
So which means that you have a 1 orientation system.
You might have an orientation preference.
Okay. What's this direction? Like, I kind of know this direction is the orientation. The method.
Tilde slash.
That it's not easy for me to tell.
I don't.
Use tilde slash.
Because I like the distribution when it gives you like the half globe, and then you can see that because it's a little more intuitive. Because I have a reflection orientation, but this it's hard when you project that to 2D.
Oh, okay, I see. So it's more like so it's a projection of 3D orientation into 2D maps.
Yeah.
Then.
So, but ideally, if
Oh, I
it's
see.
uniform, it would cover
It's like
everything.
that, like that and like that.
Yes,
Like
but flat.
flat, yeah.
Right. So, but if I think of I think of it more like this, because like if I have an orientation, I think of it, then
I see.
intuitively I can see that.
So
But then now you try to represent it in 2D. That's what
I
that
see.
is.
And this is pretty much so it's a different iteration. Is it? No, it's the same.
It's another way of displaying it, I guess.
It's like an opposite.
You have to give the, you have to have the space
Precision.
also.
Another measure of that, another way of thinking that, I guess.
So we have
Otherwise
more
it's-
particle in that
it won't be
direction,
able
so
to
precision
identify
is high.
the numerical
Statistics are probably better.
So here should be map,
Fine, so this,
and this is map, this one,
don't want more
download, map.
oh yeah, barbecue.
This you can see, we can open the sky map.
Okay.
I just wonder how our looks like.
Yeah.
Yeah,
Yeah, homogeneous. That's where it's down. So we can just list that. So I think you see the one very high here, and you have the only run the heterogeneous. And the, when you run, actually it's got control line, but not as good as the homogeneous one. I guess because it's wow. This one probably should be good.
so this
For
first model,
and
and very
this
low,
for the
and second model
model
is
that's
pretty
really
good.
good. So we use this one, the one, the good one.
Because every time you don't need to configure file on your machine program, you can or maybe they are wrong. That is on its it is in the network file.
D3?
Is it D3 also?
I think, I mean this particle, this
Okay, let's put D3. So this one is not very different from this one.
Very similar.
And we probably also can pick out this one.
This is class 1. Yeah, just one. Oh, what about class 0? Can you run in class 0 as well?
Yes, but I guess it would be pretty bad. Doesn't allow me.
No, let's see if you scroll down.
I heard it says no. Oh,
No,
here,
this
here,
one.
here.
Yeah, this one.
This is 0, 0.
Yeah.
Okay.
Mhm.
So try and block.
Yeah. little bit
the
tilted.
camera didn't do it all. Like, so it needed to be located at once.
Well, what did you do to get that?
Why didn't I?
I was it was just an online server to just bring on it. Which looks awesome. That looks nice.
I think it's just dated.
Honestly, because they can outline this other than but I think if they would have the align feature.
Right.
So exactly how
What do you think better program for that? Latest one.
I think it will.
I guess when it's good everywhere. When it's not good, then.
I think that from what I've been so far, the sort of classification and the lion looks usually easier.
But
Even
that's
you
what's
created
final one.
folders.
Yeah, it's kind of
And then I run
we
this
sort of
with their
pictures
folders.
Yeah.
Here.
But then
I
Where?
Yeah, I copy them here.
so basically the idea is
I use
just always look at what's the result in the line and this and that. Go forward.
Oh, yeah, actually I can use
What's the last one?
This should not be duplication.
that's not working specific. So these two for resource structure. This actually has access. From the PDB out.
So Appion to test is what we should use.
This here, that looks very messy, right? I don't see stuff here that we see here.
Most of the time I stuck there when mine was nice and clear.
Here you have like even
You're running video?
I haven't
Yeah, read or write directly.
Yeah. Read this one, and then
You
you do
make
this.
you made a directory called Appion to test.
Yeah.
Video. Where is it?
which institution which institution are you from?
That's just download and
From outside.
open.
Nice.
Yeah, it's very similar.
Can I ask you a stupid question?
Mm-hmm.
For the underline where it asks to do CTF correction,
Yeah.
do you do this every time? Or do you only do it for
I
the
would
first
apply
one?
CTF correction because if you don't apply CTF correction when you merge data and you're at different defoci, if you remember the CTF, then you're going to be merging and mixing phases, and then you're going to be limited. Right, so you'll be limited to the first, around the first zero, which would be in the order of like nanometers. So that's great for class. The negative stain, you don't even. So if you're doing negative stain in Reliant, then don't bother. But if you're doing crowd data, you would definitely need to CTF correct. I mean, you would have to estimate at some point and then correct.
But
CTF correction you already do in Appion, right?
Right.
How we usually
So
do it.
normally yes, but you may, if you run CTF estimation more than once in Appion, it'll seed with the previous number to do the second round, etc. But why I mention that is that just because you do CTF estimation doesn't mean it estimates correctly, and you could apply wrong CTF estimation. Let's say you have the wrong pixel size, you have the wrong whatnot, and then wrong magnification. You just fed wrong information to it, and it might fit, but then it may not be optimal or account for the data.
I can send you, maybe I have some.
So what do you do? Well, back in the day, some people actually looked, at to make sure that the fits are actually reasonable, or if there's a big mismatch. But now these days we statistically just brute force through it, hoping that we collect enough data that more or less it's okay.
This is,
The first one or the second?
no,
No, the first
so,
run.
Oh, it's finished.
Yeah.
Very few people do multiple runs,
So refined
but
it down.
they might, it's really depending on the data. So if you're very, it becomes a problem if you have sparsely populated micrographs. Like you only have 1 or 2 particles per field of view, and you just don't have much signal, therefore you'll have poor estimation. You could have beautiful looking CTFs and just completely mad of aggregated protein. Right. Right, but it'll give you great signal, and if it's on one plane, it'll be perfect.
Oh, nice. Yeah, what the intercept.
Yes, exactly.
Only the
Yeah.
visualize.
I'm having fun moving along. Where is that? Almost done extracting. Okay, it's about a good time. Does anyone have a project they want to volunteer? What project I should look at? We could just go over some results, just see where everyone's at.
Working.
Anyone want to volunteer? Yell out a group. Group
4.
4. 4 is let's live. Go group 4. Okay. So let's see if I can interpret that. So group 4 imported particles. So if you look at, there's different views. So right now, if you go into this view, that may be helpful because it organizes the data tree. So the workflow of what's going on. Certain things I didn't go over is that how CrowdSpark manages things. If you go all the way back, you can see there's different projects, and then within the project are different workspaces. And something that might be useful, let me just pop into my group for a second. So I have a couple different workspaces. So something that you can do is you can start a job, and you can link the job to another workspace or move it. So in case you started a job in the wrong area, and so you can move things within project. And every time you start a job, it sequentially numbers them. Okay, so let's go into group 4 and just let me see if I can interpret what was done. So they started off with importing micrographs. You can actually determine the CTF parameters. You can see high tension, well, the CS. So this must have been collected on a CS corrected system. Why? For Krios, typically our CS is 2.7 millimeters. In this case, when we're collecting on an image corrected system, we use some nominal CS like 0.001. So in this case, I assume this was collected on Krios 2 in this facility. In terms of amplitude contrast, sometimes people vary this. Right now, default, we are somewhere around 0.07. Sometimes some programs use 0.1. Okay. This is the pixel size, and then this is the box size. So it's 1.7 angstrom per pixel, and it's a 144 by 144 pixel box size. Not too unheard of because this is the same thing that we're using in Reliant. And then you can get a snapshot of the particles, the particle count here. Something that may be also useful, then you can always find what input you actually use in that tab and the explicit path in anything we use. Okay, great. So then next was a 2D classification run, 20 iterations. In this case, they did 15 classes, as you can see here. And not anything too special. Something that this is saying that effectively CrossSpark thinks you only need a couple classes to account for all the views here. You can download this like PNG or like this file, or you can just click and drag, and so then this becomes a nice file that you can use for your presentation if you just want to display certain things. By default, that you see most of your runs went for 20 iterations. Is that located in here? So the number of iterations by default, typically 20 is enough, but I mean, depending on your signal to noise, you may need more iterations. So there's certain default parameters that we didn't change, and it's located here, but in case you wanted to, you could always go and have more iterations. The main thing that many of you have noticed when you're doing classification, if you're doing classification, the K is variable. So do you need 1 class, 2 class, 10 classes, whatever? That's really up to you. Particle selection, so then they select it, so then this is clear where it says how many particles were selected and excluded. And this makes sense because you can see particles with secondary structure features, and this, you know, who knows, didn't align very well, perhaps. Ab initio, and they also did heterogeneous refinement. In this case, they chose 2 classes. Ab initio, something that some groups found that applying symmetry didn't really work out very well in ab initio. So enforcing symmetry above C1 is not recommended for ab initio reconstruction. They chose 2 classes. Were you able to download these 2? Did you look at them? It's in Chimera. So then you clearly saw one was better than the other. You can sort of visually see that here. But sometimes what would happen is, like, just because if you specify too many classes and say, like, I want ab initio 85 classes, well, one class will have the bulk of the particles, and you might have other classes, because by virtue of you calling for so many classes, might only be populated by like 50 or 2 particles. And then, of course, the reconstruction is not as good, but that could be an artificial separation. So there might be a situation where you might call for many classes, but decide, despite that, I'm actually not going to pick one class over the other. I'm just going to just continue with all classes. So just because you do a sorting step does not necessarily mean, I mean, you can bin particles however you want. So just because you bin them in 2 bins doesn't mean that one might be better than the other. You might decide that I want everything. Okay. Or you might decide, like, I binned, and I'm going to use ab initio in a different way. So sometimes you may have a situation where you have complete angular coverage. It just so happens one view is 10-fold more than any other view. You can use ab initio to do multiple rounds of ab initio sorting 2 classes to whittle away the overrepresented class, such that by virtue of sorting it out, you're sorting out a class with more uniform angular coverage. We've done that before in a particular test set. So there's different ways that you can make use of these same features for different purposes, just beyond making an ab initio model. Something that's a little bit different in Reliant than CrossSpark. So Reliant has classification. CrossSpark doesn't have classification per se. It has heterogeneous refinement, meaning it'll try to refine based upon multiple input models. But in a sense, you can see that this is a potential classification, or you can even use ab initio multiple classes as a way to do some sort of separation of particles. But in the case of heterogeneous refinement, what you're doing is, with multiple models, it's trying to do refinements. It's doing refinements up into a certain point. You can see the FSC curve looks a little bit odd because it, for efficiency purposes, is doing your refinement binned. Right? This is probably going to be cut off at 128 pixels, or something like that, or binned by a certain amount. So then that means if you do heterogeneous refinement, then you'll have to choose these classes again to do a homogeneous refinement, which is one of these located here, which is probably J8. Well, yeah. So then this, so you can see like this. In red, it highlights the inputs, and blue is what I'm selecting. So J8 is using this heterogeneous refinement. Okay, great. I could also see that by just looking at the inputs right here. And in this case, D3 symmetry was imposed. Fine. And if you see as it's going along, you can go to various checkpoints and see the various iterations. And you can see went to 3.6 and the B factor of 117, very respectable. There are other things that are in here that we haven't really made use of. Like, for example, you can do some post-processing. So some people have noticed that there's a representation of angular distribution, and in this case, this is pretty good because there's equal coverage across. Another way of assaying if you have preferred orientation would be 3D FSC. So in that case, it does FSCs in cones, different cones, and then in basically directional. And so then you have a better idea of, do you have better resolution in a particular direction than another direction. Res log analysis is something that may also be useful. Let's say you have a target resolution. So what this will do is it will do reconstructions in different subsets. Like, okay, if I had 1,000 particles, what's that resolution? 2,000, 3,000, 6,000, etc. Then you could extrapolate, well, if I added more particles, would I improve resolution? So if you're plateaued, let's say if I'm at like 4, I'm at a particular, and then I'm my particular slope. Now if I want to get to 3, I need 500 billion particles, then you would understand, well, you're probably plateauing. So it may not be worth to collect any more particles, because if you add of like kind, then you're at a resolution limit. Or if you say like, well, I added 1,000, I'm at 5, I added 2,000, I'm at 3, okay, great, I'm just going to collect more because I'm at that slope. I haven't plateaued yet. I can add a few more, and I can definitely improve resolution with minimal overhead. Caution behind that assumes you're adding of like kind. So I can say like, oh great, I just have to add another 1,000 particles and I'll increase by another angstrom, and you add another 1,000 particles of 20 angstrom quality particles. Well, you're not going to improve resolution in that regime because you're just adding more particles, not good particles, you're just adding particles. So the main thing to note is if you're doing a reslog plot, you will have to take into account your attrition. So if you say, I had a certain number of particles, I cleaned away 80% of it, and then this is what I'm doing a reslog plot of, then don't forget to go back like, okay, so if I collect of like kind, I will have some attrition to get that. So then you may have to collect more particles than just that plot. So you've pretty much seen the Crosspark interface. Does anyone have any questions about that? You can see they're slightly different between relying on Crosspark. There's certain advantages and disadvantages, and it processes data a little bit differently. Both instances are still kept open, so you can play more with Line, play more with Crosspark, and the intention is that a lot of these additional tools that were not in the tutorial that you do make use of. Okay. Does anyone have any comments, any questions, anything particular about what they've been seeing here? And you are also welcome to process other data. We only have a few data sets within the instances, but then that will help expand, trying to, like, if you ever wanted to go back to micrographs and go through instead of the particles we've given you, or you want to go back to the particles and then do more of classification. So hopefully this fills in more of that pipeline, where if I go back to the original slides, here we go. So now between Appion Part 1 and 2, then you have a conception of, okay, what you do during your Legion session, what Appion can do for pre-processing, what you're going to be able to do in, like, on the fly for feedback, or after your session for a little bit more in depth, and then what can be done with your home computing, or
In this case, we use Amazon Web Services such that you can call certain resources on demand. And then for this workshop, we're a little bit economical in what we're doing, but per chance, if you're running out of resources, you just say, I want a larger instances. I want more GPUs. I want more space. All that can be purchased on demand. Or if you're using your home institution cluster, it might be a matter of queuing or waiting or resource sharing in some way. But that is where you can get more into 2D and 3D criteria and then 3D refinement. And really, that is the best criteria. So if you're trying to sort out data, you eventually need 3D feedback, right? Because it might not be so apparent in 2D class averages if you have preferred orientation. It might not be so clear just by 2D classification if you have heterogeneity. Maybe you can tease that out. It really depends on your sample. Also, it's really a matter of preference, but my particular preference is that don't be so severe in particle selection early on, and unless you have prior knowledge or orthogonal knowledge, it's okay to carry data forward and then try to do more sorting later on. In addition, don't feel that you only have to do one step once. Like, this has to be the perfect CTF and I'm only going to run it once. This has to be the perfect particle picking, I'm only going to run it once. I'm going to do only one refinement. That's unlikely to be the case unless you actually have really worked out your data set or are working on, like I say, the test data set that we're working at. On most data, you'll be working at it multiple different ways, and you might be going through different points. In this particular workflow, we are already assuming that you're making use of this pre-processing such that I did mention if you want to do particle polishing and the rest, you do have access to the movies, and then in that case you probably would want to go all the way back because by default we only do 5 to 5 patches. Right now people have shown that a balance between time and GPU resources, 7 by 7 might be more towards where people may want to go. Any more than beyond that, well, it just requires GPUs to be cheaper. I mean, you potentially could go 11 by 11. You could go 25 by 25 patches. It really depends on how much computation you have. Is it worth it? And in addition, does your data have enough signal to noise? Because if your data has very low signal to noise ratio, by doing more and more of these, per region, per particle corrections, your estimation might be wrong. Similarly to CTF estimation, I made that example. If you had one particle that would go to 1 angstrom resolution reconstructions in that whole sea of buffer, there's not enough signal to noise to be able to get a good CTF estimation. That micrograph would look horrible if you just use CTF as a criteria. And if I had a whole bunch of aggregated protein, again, that's a lot of signal to noise, great CTF estimation, doesn't mean that is reflective of what your final reconstruction will go to. I can take a nice picture over continuous carbon and get great CTFs, but doesn't mean I have any particles of use in that micrograph, right? So then that sort of speaks more towards what we're trying to do today is fill in the rest of the criteria, give you more of that 3D feedback to understand your data sets, your samples, such that you can prioritize that and then that you can spend time on it wisely. We definitely made use, so hopefully also to wrap up, you know how to use Globus to get your data, where your data is in the pipeline. And right now we were using Amazon Web Services, but there are other services like Cosmic and other on-demand services that you could make use of. So I'm going to wrap up here with the Appion workshop. You don't have to leave. We actually have our annual user meeting. My assumption is that very few people beyond the people in this room will come for the annual user meeting. However, at 3 o'clock we have a picnic upstairs, and that'll be catered. So by all means, it's a whole NYSBC picnic. You're all welcome to attend. The instances you're running are still going to be on for another couple hours. So if you just want to stay in the room until the picnic, by all means do so, and we'll be around to answer some questions. But in terms of Appion Part 2, we're going to end the stream now and we'll convert. Okay?
Thanks, Ed.
could have